Hallo, hallo.
Good morning, everyone. We'll start soon. I'll just wait a little bit longer because there's still people getting into the session. Okay, let's get started. I'll start by sharing my screen. Okay, and I'll switch to the presentation. Okay, so can everyone hear me? Just put something in the chat. If so, then yeah, okay, excellent. All right, thank you. So let's get started with machine learning with Python. To avoid confusion, this is the same as Python for machine learning. The reason why I decided to gradually change the title of the training is that there were some misconceptions about it, that it would be about Python, you would need to do machine learning, while actually it is about machine learning, and you happen to do that with Python. So it's just to, let's say, put things better into perspective. Okay, so this is likely not going to work anymore because I can't remember whether I updated this. Doesn't matter, because what I will do is tell you what it does and also put the link in the chat. So if you would use that QR code or that shortened URL, you would end up on this particular web page, which is simply a short description of the learning outcomes and a tentative schedule of what we're going to do. That is all very interesting, but obviously the most interesting thing is actually the link at the top right corner, and that brings you to a GitHub repository, which I'm showing you now. And this GitHub repository essentially contains all the training material, so the presentation I'm going to use, but more importantly, also two directories, one with source code and the other with hands-on material. So the hands-on material is something that you can try for yourself if you like, so that you can actually do things gradually. Typically, the notebooks come in 3 formats. So you see that each name is preceded by some number, and then there is a suffix which actually says what it is about. So basically, there is always the complete notebook, which is of course boring if you want to practice yourself. There is also a lazy version, which basically means that you kind of click through it. And then there is a version for the more courageous among you who actually want to figure out more for themselves. So that's true for each of the notebooks. We'll get to those later on. There is also a source code directory, as I mentioned, and that also contains additional source code, probably also, well, certainly also about things we won't be able to cover today. So this is one of the 2 repositories which I'm going to use today for certain. The other one I may be using, we'll see. That also depends a little bit on your feedback. So I'm going to post the link to that webpage in the chat, so you have access to that. Of course, feel free to fork the repository, clone the repository, whatever you feel comfortable with. All the material is publicly available, and there is a license agreement, so you know what you get yourself into. Okay, the third slide is basically, again, the QR code, but now in this case for following us on LinkedIn. So this is a training which is co-organized by the Flemish Supercomputing Center, VSC, Vlaams Supercomputing Center, and the other party involved is EuroCC Belgium, so the National Competence Center on HPC, HPDA, AI, and quantum computing. So both of these organizations actually are organizing this particular training. Okay, so before we dive in, a few practical things. The more interactive this is, the more pleasant it is for me, and hopefully also the more productive it is for you. So feel free to type questions in the chat at any time. I'll probably be able to keep an eye on the chat during the whole session. With this setup, it usually works. I might choose to answer your question a little bit later if that fits better in the flow of the training. But at any rate, I'll get your question answered. All right, so machine learning. I probably don't need to convince you anymore that machine learning has made quite a lot of strides in recent years, and that is due to a number of factors. So a very important factor in the early days of, let's say, the current boost of machine learning applications was, in my opinion, mainly due to large data sets, but also data sets of high quality. High quality in the sense that suddenly certain organizations got access or had to their disposal data sets which were labeled by humans with pretty high quality. What do I mean by that? For instance, I can give you a couple of examples. So basically, Google sits on a huge database of images. And some of us who are keen photographers or who have a touch of obsessive compulsive disorder actually label our images. So that makes it an interesting training set if you're doing object identification, for instance, because there will be a significant number of images that have been labeled with the subject that they actually represent. So that is one example. The other example, if you think of natural language processing, is, for instance, sentiment analysis. And of course, if you are Facebook or Meta or whatever you want to call it, or your Twitter or X, then you again have a huge data set of posts, and you have a fairly good idea, without even doing textual analysis, whether that was liked or disliked by members of that particular service, because we like and we dislike and whatever tweets or Facebook posts or whatever. And that was, of course, a major benefit to all kinds of machine learning attempts in the early days. And now, by early, I mean, let's say 2010, around that. Also, of course, another factor which contributed quite a lot to this, let's say, explosion of machine learning applications is, of course, the availability of relatively cheap compute power. The emphasis is, of course, especially lately on relative, because GPUs have been extremely expensive lately, especially the latest generations. But let's say 10 years ago, GPUs were not that expensive, but gave you significant performance benefits as compared with CPUs. And then, of course, we get to the third pillar of this story, and that is, of course, some progress in algorithms. Basically, that progress has been maybe the least significant in a sense up to a couple of years ago. So if I looked at the machine learning landscape until, let's say, 2015, 2016, 17, then I'd say, okay, it was just more of the same of what was already done in the 90s of the previous century. So not that much had changed. There were some newish architectures, but still they leaned heavily on algorithms that were proposed in the past, but that were for practical reasons unfeasible, in the sense that you needed so much compute power or much larger and better quality data sets than were available at the time. But things changed also in that respect a little bit, with some rather neat new architectures, which, for instance, are employed in large language models. So that definitely changed as well over the past, let's say, 5 to 7 years, something like that. Okay, So, of course, I don't need to convince you either that there are many interesting applications, both commercial and scientific. So, what do I mean by that? Commercial applications, I'd call the OpenAIs of this world, who make significant amount of money or lose relatively small amounts of money on making machine learning models available for services like chat, like image generation, and so on. And of course, there are other applications. You can think, for instance, of generative AI in applications such as Lightroom or Photoshop in the realm of photo processing, but also, of course, in video processing, you have similar applications. So that is definitely a very good example of commercial applications where either small or significant amounts of money can be made with such services or such algorithms. And then, of course, also more interesting, there are also direct applications in sciences, which are very much outside of the domain, the classic domains where machine learning would be applied. And then you can think, for instance, of astrophysics, for instance, where significant progress has been made by employing machine learning models for solving or for representing systems that would normally be solved with partial differential equations. That goes for any domain where these these equations are relevant. Astroplasma physics would be one, but also, of course, computational fluid dynamics and so on. And of course, we should certainly not forget about quantum chemistry, where potentials are now often the result of machine learning algorithms rather than being computed ab initio from first principles. So those are very interesting and promising applications. Okay. One of the things that bugs me a little bit, to be honest, is artificial intelligence versus machine learning and so on. And nowadays, everything is artificial intelligence. Yeah, okay, it's a catchphrase. Good for you, but I mean, there is definitely a difference. And what we will be talking about today, and most of the things, if not everything, you hear about, okay, everything is a bit too short. That would be a bit over the top. But many things which you read about in the press and also in scientific literature is actually just machine learning, not artificial intelligence. Personally, I like to make the distinction because artificial intelligence is a much broader field and encompasses much more than just machine learning. And what companies like OpenAI and others are doing is still just machine learning. So basically, well, okay, let's keep terminology straight. Okay, so if we have a look at what machine learning actually is or can do, then we should maybe have a look at how things are, what tasks you can actually do with machine learning and how the field actually is divided up. And one of the things which is very prominent and which is also in large part what quite a number of applications are using is supervised learning. And supervised learning, again, falls apart into a number of categories. One of them is regression. So that basically means you're trying to predict a numerical value. A numerical value or many numerical values, but at least it's all about predicting numbers. And then on the other hand, you've got classification, and that means that you're not predicting numbers, but rather categories, labels. And you can argue that in fact you can represent labels by numbers, but we'll come back to that later and argue that that may not be your best approach for a number of reasons. So we make the distinction between regression and classification in supervised learning. Why is it called supervised learning? Essentially because you've got, as your training set to do machine learning, you've got examples that contain both input and output. So for the training set, you know the outcome that your algorithm should provide. Okay, so that is sort of easy. Well, it's definitely not easy, but it's the easier kind of machine learning task. Another one is unsupervised learning, and as you can already guess, that means that you don't have these convenient input-output pairs. So basically you need some other criterion and other training techniques in order to get that task done, and also to assess the quality during the training of such systems. So this is already a little bit harder, and that is, I can give you a few examples, let's put it that way, a few examples of such unsupervised learning tasks. One of them, for instance, is clustering. So try to group data according to some distance measure, whatever that distance measure is. So that is something that typically you use in order to detect structure in your dataset. You want to know whether you can group certain data points together, and that makes sense in some semantic way, whatever that is. And of course, that will be heavily influenced by the distance measure you use. The distance measure meaning how much does one data point resemble another data point. Another example of unsupervised learning is association. So basically, you're looking at a large data set and you want to see whether certain things co-occur frequently or whether you can predict that. And this, of course, very classical application is what supermarkets do all the time with your what's it called, your typical cart. So basically, they look at your shopping cart and they say, okay, if someone buys, I don't know, peanuts, that person may also be interested in something to drink, to serve with it. So basically, you will get the next time you go to the supermarket, and you will actually get some vouchers that give you some benefit when you buy some drink, whatever. Another very interesting one, and again, I'm giving real life examples, but probably you can translate this easily into scientific examples in your specific domain. Another one is link prediction. So basically, now in this particular case, our data is related in terms of a graph. A graph, not in the sense of a plot, but a graph in the mathematical sense. So a thing with with vertices and edges. And what you want to do is you have a number of vertices and edges, and you want to predict whether there could be an additional edge between two given vertices. Okay, and this sounds very abstract, but what in the end of the day it boils down to is that Facebook, for instance, is giving you friend requests because they analyze the friend graph of their users, and they note that if I'm connected to person A and person A is connected to person B, I might want to connect to person B as well. And of course, it's more complicated than that because they don't just look at a single edge. They look at many edges and compute probabilities. So that is another task which falls under unsupervised learning. Also, very useful application, especially for science, in unsupervised learning is data reduction. So typically in machine learning tasks, we deal with data that has many features. And the question is, are all these features required, really required to describe our data? The answer to that is often no, not really. A subset maybe a linear combination of features is actually the only thing which is required in order to describe your data set. So then, of course, what you try to do with dimensionality reduction is to go from your original feature set to a reduced feature set, which is typically a lot smaller. So that gives you, if you like, some sort of data compression. But you can also use the same technique in order to perhaps better understand your data set, which features are in fact salient and which are not that relevant. So that's something that data reduction can also help you with. And in cases of extreme reduction, what do I mean by that? Well, reduction to 2 or 3 dimensions, it can also help you to do visualizations of high dimensional data. And it might help you, maybe, to detect structure in your data set. So that's in a way related to clustering as well. So both of those are in fact intended to try and understand your data set better. All right, and then there is a third type of task that is also pretty important. Now, for instance, if you want a self-driving car, you would need most likely something like reinforcement learning. So essentially, that has been applied by companies that make self-driving cars. That is one application, but another application, for instance, is DeepMind's AlphaGo, and I prefer to explain it that way because it's a little less bloody. So basically, what do you do? Well, essentially, you let an algorithm play Go against a number of opponents that are also algorithms, and basically you make the algorithm learn from its mistakes by either rewarding it when it did well, in other words, it won, or punishing it, quote unquote, if it actually did not that well, if it lost. And of course, you will understand why I phrase it this way, why I give this example for reinforcement learning and not self-driving cars, because you can imagine what a failing self-driving car algorithm does, and that is indeed a little bloody. So let's not go there. Okay, so another few examples. I already gave you a few, but maybe some that are not really that obvious, that are actually regression tasks. So something that is quite interesting is colorizing black and white images. And you will see regularly on the World Wide Web, also on LinkedIn and so on, you will see posts of historic photographs that have been colorized. And of course, that you can argue that from a historic point of view, this is maybe deontologically not correct, methodologically not correct, but still it helps us make, or it helps history come alive a little bit for those of us who are somewhat visually inclined. So why is this regression? Well, simple. Each point at the end of the day is a set of 3 numerical values, red, blue, and green. And you start with one value, which is essentially the grayscale value, the brightness of that particular pixel. So essentially, you are predicting numbers. You are predicting RGB codes for each individual pixel. So that makes it a regression task. This is an example of classification, again, visual classification. So basically we have a picture and we want to identify objects. So each object, in this case a dog and a hat, this is very unfortunate for the dog. I wouldn't like to be the dog here, but okay. So basically, we are not only identifying the object, but we are also classifying them. We are labeling them with whatever the algorithm thinks that the object is. And in this case, of course, I would agree that there is a dog and there is a hat. So this is, let's say, well done. Note that there is even more detail. The algorithm even detects that it's a hat with a wide brim. So this is classification because there is a category dog, there is a category head with subcategories, whatever, but in this case at least a white brim. This would be a playful example of reinforcement learning. We're all familiar with the game. What's it called? Pong, I think. Yes, Pong. Or Breakout. And essentially you move a bat, that's that red arrow here at the bottom of the screen. You move that left and right, and you can even accelerate that. So you can do that with different velocities and also make it accelerate. And that makes the ball, which is here. Where's my mouse, by the way? Oh. The ball, the little ball here, makes it move when it gets hit by the paddle. And then you hit the bricks up here, and you have to make a hole in it and kill as many bricks as possible, or destroy as many bricks as possible before the ball actually goes through. So you know the game, it's a classic one. And this is a typical thing which you could do with reinforcement learning. So basically you start off with something, a paddle that moves randomly, and then gradually by playing many games and adjusting the probabilities of how this thing is going to move at each point in time, you actually get something that plays quite well. And the interesting thing about this is that there is really no physics involved in the training, but the only thing this was trained on are actually images of this particular game. So essentially screenshots, if you like, or video captures of a running game. And that was what the algorithm got, well, the training algorithm got to see in order to do the reinforcement learning. So that's actually quite interesting as well. Okay, then yet another example, but now for unsupervised learning, is clustering. And in this particular case, that would be crime prediction. And that was used doing k-means clustering. So this is an example which was done. I don't quite recall either by the Indian police themselves or a research group that collaborated with them. And that way, the red circles actually represent geographical areas where certain crimes are more prevalent than others. And so that would help the municipality police in order to, let's say, concentrate on such hotspots for certain crimes and try to do something about it. Okay, and then of course there is quite a lot of applications in science, in chemistry, as I already mentioned, but also in computational fluid dynamics, in image processing for Earth observation, and so on and so on. There are quite a number of applications out there, and they're growing as we speak. Okay, so that is a little bit of an introduction. So let's concentrate a bit more, because it's a very wide field. So let's concentrate a bit more on what we're going to talk about today. So which machine learning algorithms are we going to discuss, and what is out there? So one of the things we'll definitely talk about is regression. And as you can see, there's a long list here of regression algorithms, like ridge regression, support vector machines, random forest, multi-layer neural network, deep neural networks, etc., etc. And so essentially, as I mentioned, you are going to try to predict numerical values. And then there's also classification. So for instance, naive Bayes and support vector machines and random forest and multi-layer neural network and deep layer neural networks. So notice that many algorithms can be used for both tasks. So you can, of course, with some changes, make them useful in the context of regression, predicting numbers, or classification, predicting labels. Essentially, it is similar. I won't say it's the same thing, but it is similar. So hence, because that's the case, we can actually employ the same basic algorithms and tune them slightly in order to either regression or classification. And we'll also talk a little bit about clustering. And in there, again, you have many clustering algorithms. So what we'll concentrate on in this particular training is for regression, we'll talk about rich regression. For classification, we'll talk about naive Bayes, but also deep neural networks. And we'll also talk a little bit about k-means. Why do I do that? Why don't I just talk about deep neural network and that's it? Because if you look at applications, then deep neural networks are fairly sophisticated. Fairly sophisticated means that training times can be significant, and also the required data is quite significant. And of course, there are many problems that don't require that much machinery, that can be solved equally well by much simpler algorithms. And that's something that I really want to draw your attention to, that it is not because there is something like deep neural networks, deep learning, that every single problem should be tackled with deep learning. That is absolutely not the case. There are many instances where classic quote-unquote algorithms, so pre-deep learning algorithms, actually perform as well or even better. So it's something that you need to be aware of because people typically don't tell you, but it happens to be true. And if you look at the literature, then you will see quite a number of examples of that. Okay. However, everything I will be telling you about, not about these algorithms, because I actually will hardly talk about these algorithms, but this will be more about methodology, and the methodology which I illustrate using rich regression or naive Bayes just translate one-to-one to deep learning or to support vector machines, or pick your favorite method. Okay, so as I already mentioned, this is in large part, about methodology. And then we have to think a little bit about potential issues when we think about machine learning projects, or if you really want AI projects. So Gartner has done an analysis, as they typically do quite a lot, and they looked at companies typically that started machine learning projects. And actually, according to their study, 85% of all projects that are started, in fact, fail. So that means you have a success rate on average of just 15%. It's not that much. Okay, so that's one issue that you should keep in mind before you start your next machine learning project or your first machine learning project. We'll talk about why things can go south later on, so no worries. And then, of course, there's also the ethical thing. And so, for instance, at some point, Amazon had an algorithm that would automatically assess employees, give them a score, and based on that score, also write them an email telling them that their services were no longer required by the company. Do you think that is ethically sound or not? I leave that to you. But basically, there are people who have their doubts about it, and I'd be in that category. Of course, this is a quite extreme example, but as you may be aware, the European Union actually has legislation in place which is pretty strict about the ethics of machine learning and AI algorithms. And in fact, it's the most strict set of rules, most strict legislation that is in place in the world. So there is definitely reason for concern. And of course, the first thing you might think of is Battlestar Galactica kind of things, where machines take over or try to take over. But yeah, there are other ethical issues as well. So that's something to always bear in mind. It might seem less of an issue in science, but still it's always good to have that in mind. Okay, so as I already mentioned on the previous slide, I would talk about reasons for why things go south or can go south, and there are quite a lot of them. Most importantly, maybe there is asking the wrong question. So basically, an analysis upfront of the problem you want to solve, and this is on the one hand true in a business case, but also true in a scientific setting. So what question are you actually going to try to solve? Is it the right question? So that's the first thing to try and identify. And related to that is, of course, trying to solve the wrong problem. So you might think that a problem is in a certain area, and it simply is not. Think of process optimization. You're optimizing for certain parameters. It might be that your performance is much more influenced by something different, like, for instance, a supply line or something like that. So basically, that is also something that you need to keep in mind. And then a very important one is not having enough data. So typically, machine learning algorithms are data hungry. And if you don't give them enough data, if you don't have enough data, then you are not unlikely to build a very expensive random number generator, which benefits, well, the electricity companies, but that's essentially it. And then, of course, you should have the right data. So there may be bias in your data. And again, let's just take a real-world example in order to get the point. So essentially, if you look at, for instance, natural language processing, and you look at bias, if you just pick something randomly from your favorite social media platform, not to mention X, then you might find a lot of data or a lot of conversations that are heavily biased. And that, of course, will mean that whatever you train on it will have that bias as well. So that's one example, but also another example. Let me give you another example out of the scientific domain. Suppose that you're doing CFD, computational fluid dynamics, and your training set consists totally out of examples where your flow has no turbulence. Okay, that is very likely going to mean that if you go into the realm of parameters that then give rise to a flow with turbulence, that what you will get is total nonsense. So that means that you would not have the right data in order to complete the project successfully. It's also possible, and that might seem a little bit weird, but you might also just have too much data, in the sense that the data itself is getting inconsistent. And then, of course, again, you are in trouble. That might mean that you actually would have to, let's say, segregate the data and maybe train two models, one for each mode of your process. That is really, there is nothing wrong with such an approach. And then, of course, you need skill sets. So essentially, you need people who, on the one hand, understand, well, they need to understand quite a lot of things. We'll come back to that again on one of the next slides. But you need people who understand the problem, and that's your domain problem, but also who understand the mathematics of machine learning. They also need to understand how to deal with data and so on. So it's not entirely trivial to find the right people for such a project. And then, of course, there is also using the wrong tools. You might be using either an algorithm which is not okay, or data filtering which is subpar or whatever. So things like that. And then, of course, there is not having the right model. So essentially, if you only know about linear regression, anything nonlinear is definitely going to escape you. So that again is quite important to have the right model. And all of that is not particularly trivial. And then the last thing is not having the right measures in order to, on the one hand, assess success of your training, and on the other hand, assess success in the deployment. So that is referred to as a yardstick and is essentially also a requirement of each successful project. So these are things which you should really bear in mind if you start off on a new machine learning project, that these are all important things to keep in mind. Okay, so this is also a little bit about Python. So there are frameworks, and of course there are many programming languages which you can use in order to do machine learning. The most popular at the moment is, I think I can safely say that, certainly Python. You can do machine learning with R. That is entirely possible. You can do it directly in C++ if you like. That's also possible. Also, Julia nowadays is a contender. So all of these programming languages can be used to do machine learning. In fact, I would say that machine learning is sort of independent of the programming language you choose, because in most cases you are going to use some framework. And that framework happens to have bindings to certain programming languages. So in that respect, choosing a programming language for machine learning is maybe not the right point of view. You should look at an interesting framework and then decide on the language based on the bindings that framework has with various languages. So we will be talking about Python in this case because I think it's a very good choice. Not only because, as far as I know, most of the relevant machine learning libraries actually have Python bindings, but also because Python is, of course, a very good language in order to do data extraction, data collection, and also data filtering. That is significantly more difficult in a language like C++ because there are not many libraries out there that actually would do the job for you. So that is why I would personally, at this point, recommend Python as a language for machine learning. And you might argue, yeah, but Python is slow, and yeah, I do agree. But on the other hand, you're not using Python for your core machine learning tasks. What you're going to use is a library, like for instance scikit-learn, like PyTorch, like TensorFlow, and so on. And these languages, you would say, okay, that's also Python. No, it's not, because it's just a layer of Python on top of libraries that are actually implemented in some high-performance computing language, programming language, such as C++, or perhaps others like Rust or Fortran or whatever. So that is basically the point. We will talk a bit about scikit-learn, and I'll explain you why we do that. You might say, okay, scikit-learn, yeah, but it's only for classic machine learning. So basically for the old style stuff, such as rich regression and support vector machines and all that kind of old-fashioned stuff. Yeah, that is, of course, true. That is what scikit-learn is going to do for you. But on the other hand, you will see that scikit-learn has some interesting stuff besides algorithms per se that make using it in a deep learning project combined then with other languages, with other libraries, quite interesting. So that's why I will talk about scikit-learn anyway. And the other motivation, of course, is what I already told you, that many problems can actually be happily solved by support vector machines, by rich regression, by logistic regression, and so on. The very classic algorithms which have been around for almost half a century now. Okay, so PyTorch, TensorFlow, Keras, etc., are mostly dealing with deep learning, and we'll of course also touch upon those. So scikit-learn we'll talk about Keras, and we'll also have a look at PyTorch as well, a little bit. Okay, so the point is, of course, that the major skill you want is in understanding the algorithms, because this is a software landscape that evolves quite rapidly. And so essentially, you will realize after a while that the framework which you use is not the deciding factor. You should choose a good one, but that differences are typically not that important, and that it's also not very, very hard to switch from one framework to the other, at least conceptually. If you have a huge library, you're not going to be happy because you have to rewrite a lot, but at least conceptually, it's not that hard to switch from one deep learning framework to another. Okay. A very important thing in machine learning and also in data science in general, by the way, is the concept of data pipeline, and a major problem that determines the success rate or failure of certain projects is indeed problems in that data pipeline. So it's important, in my opinion, to spend some time on data pipelines, because it is something that is, in my experience, typically underestimated. Underestimated both in terms of importance and also in terms of effort required. Because data ingestion is typically already a non-trivial task. Your data may come from many sources. They can come from a single source or multiple sources, and those sources can be the same or they can be different. For instance, you might be learning from a lot of comma-separated value files, or JSON files, or XML, or HDF5, whatever. But basically, that is kind of easy. Your data might also reside in relational databases, which might make a lot of sense. But yeah, then you need a way to get your data from your database into your data set, your training set. There are a couple of ways to do that, but it's not so trivial. You might have a relational database, or you might have a NoSQL database, so essentially a database that's not relational. It may come from the web, etc., etc. So that already requires some effort in order to make sure that you can read your data, that you can actually ingest your data. And that is why I personally like Python as a language for this, because Python has libraries aplenty to do interaction with any of those, on the one hand, file formats, or on the other hand, services like relational databases or web services. Okay, so one of the things that can definitely help you is, for instance, pandas, but also frameworks like Pydantic if you must, and if you need type checking and so on, and others. Okay, so somehow you got your data. Great, that was step number one, but it doesn't end there in your data pipeline. The next step is you need to do some cleaning. One of the things is to check for outliers. It might be that you have measurement data of a process or a certain instrument, and all of a sudden you get a value that is complete and total nonsense. A negative temperature, for instance, or a temperature which is way too high, which is physically just impossible. And that may, of course, have many causes. Let's not go into the details, but yeah, we have data with outliers. We have to live with that. So what do you do with them? Do you leave them in your data set? Do you eliminate them from your data set? How do you detect your outlier? It's already a non-trivial question. So those are invalid values, potentially. Are they? I don't know. So you need to filter your data somehow. And then another issue, which is of course also very important, is missing values. Sometimes, yeah, your equipment just fails and you miss data for a certain period of time because you have to repair it, or you lose a connection, or a file gets corrupted, or, I mean, there are many ways in order to end up with missing data. And then again, the question is, what are you going to do? You have a number of options. One of them is to impute data. So to kind of make up for that missing data by trying to guess what those values could have been. And there are many ways to do that. We'll discuss a few later on. And then, of course, you have your data, which is clean. At least that's what you hope. But then that does not necessarily mean that your data is ready in order to be used for machine learning tasks. Because one of the things which we know is that certain machine learning algorithms work better for data that is scaled and that's normalized. So basically for values that are between -1 and 1. So that means that you typically need to scale your data, or that you need to normalize your data, etc. So basically you need some level of data transformations. And that essentially is why I really want to talk about scikit-learn, because scikit-learn has quite a lot of building blocks in order to make your life in this respect significantly easier. It is also very important to have a consistent data pipeline, and I'll stress this a couple of times during this training. The problem is that if your data pipeline is not formalized, it's not let's say in code, if you can't run it unattended, then essentially you may have a problem. You may have a problem on the one hand, obviously, with reproducibility, which is very important in science, but you may also have a problem in production if you're running this in a company, because if there is one or more manual steps involved, that means introducing human error. And that means that maybe, again, you have a quite expensive random number generator at the end of the day. Okay. So there is a question. If you can't type it in the chat, then please activate your microphone. That's fine as well. If this was a mistake, then I'll just continue. Okay. Since the flow is interrupted anyway, I'm going to take the opportunity to paste the link again in the chat, because I noticed that there were some people who joined a little later and they don't see the chat's history. So basically, I'll post it again for those who were a bit later. So this repository contains the slides, it contains the code, it contains hands-on material, and so on. Okay, so let's talk a little bit about methodology, and let's specifically talk about supervised learning. Okay, so essentially, the first step, of course, is to select a model. And as you're already aware, there are many models out there. I gave you a very short list. The list is really very long. So you pick your favorite model, which you think is powerful enough in order to describe your data, and which is not so sophisticated that you have no hope of training it with the available data. That requires some experience. You will try, if you're starting out, you will try, you will fail, you will have to redo, etc., etc. But after a while, you develop some intuition for what is going to work and what is not going to work. Typically, starting with a random forest might not be a bad idea. That typically gives you a very good baseline. Okay, then we are in supervised learning. So basically that means we have, as a training set, we have labeled data. So we have both input and output. So what we're going to do is we're going to split our data set into two, well, in fact, into three parts. So the first part is the training data, and that is what we are going to use in order to determine the actual model parameters. So to do our learning itself, to get our random trees in the forest, or to get our trees in the random forest, to get our connections in the neural network, and so on. But we also need validation data. So basically that's your yardstick to avoid overfitting. And I'll show you in a notebook in a minute what I mean with overfitting. It's a little bit here, but just go briefly over it. So basically, this is a classification task. You have the dots and you have the crosses. And as you can guess, the dots represent one category, the crosses represent another. So I could do the segmentation as it is done in the left-hand plot. And as you can see, this is extremely complicated. But it is really, really exact for this data set. There are no mistakes here. That's great. But probably you immediately realize that's kind of nice, but sort of useless in the sense that what if I now have a new data point? It's not so very likely that this particular model, so the one which is labeled with overfitting, is going to represent data, unknown data correctly. Okay, so let's switch to the right-hand side, where it labeled with underfitting. So what are we doing here? Here we're just doing simply a linear separation. And as you can see, it will be quite error prone in the sense that there are quite a number of dots below the line and quite a number of crosses above the line. And yeah, we can tweak it a little bit, but it's not really ideal. So the optimum is likely somewhere in between. So basically we need a surface, or we use a surface, in this case a line, which is somewhat, let's call it curved, so that it basically separates the data better, but not absolutely like in the right case. So these are two dangers of machine learning, overfitting and underfitting. So underfitting means that you're trying to use a model which is not sophisticated enough to represent your data. So the model is wrong, period. With overfitting, the model is also wrong. It's way too powerful. It has way too many parameters. And there is too little data in order to get all those parameters correctly. So essentially, those are two dangers which you have with machine learning. And of course, it's very important to avoid them. And you need a yardstick in order to do that. And that can either be validation or cross-validation. Yeah, it's one of the techniques which you can indeed apply. Try to smooth the overfitted data. That is definitely an option. There are many techniques to deal with overfitting, but typically if you have overfitting in a machine learning task, then typically you will notice easily using validation data. Okay, so that's for training the model, but that's not all, because here we are using data during the training process. We also need another yardstick, which actually tells us how well did our training model work, how good was the model it produced, on unseen data. And that's our test data. So basically, test data we require, and we never, ever, under no circumstance, use it during training. It's only used after training to assess how well the training actually did. And then retrain it, no, that's not really an option, because then you're starting to use your test data, and that is something that you shouldn't do. Okay, so in production, of course, you only have input, and you should predict the output. So again, the training set, your data, gets split into three parts. Training data, test data. Never look at test data during training. And for the training model, you can either use cross-validation, or you can split it again into two parts, training data and validation data. And then use the validation data only to assess whether you're overfitting or not. Optimize parameters. No. So basically, to find the optimal parameters, what you typically do, of course, that's the aim of your training. So the training itself should avoid overfitting and underfitting. Well, should avoid overfitting to some degree. That's why you need the validation data. We'll see that how that's done in a concrete example later on. No worries. Okay. So if you want to play around a little bit with that, then there is the 010 Jupyter Notebook, which shows you an illustration of a data set where you do fitting and you overfit and you underfit and so on. That is not a classification example, that is a regression example. Okay, so let's talk a little bit about scikit-learn. So for me personally, it's a nice end-to-end framework in the sense that it helps you doing data exploration, of course, aided most likely by pandas and by some visualization library, HoloViews or Matplotlib or Pyplot, whatever you want, doesn't really matter. It also helps with data pre-processing, again, perhaps helped a little bit by pandas. So it helps you to deal with cleaning and cleaning data and missing values. It helps you with normalization, so the data transformation and so on. And then, of course, there are quite a lot of algorithms, and scikit-learn will also do the training of those. There is infrastructure for testing the results, as we will see. And of course, you can turn the whole thing into a deployed application, if you like. So as I already mentioned, that's classic machine learning only. So yes, it does neural networks. It does multi-layer neural networks, but I wouldn't recommend doing deep learning with that because there are much better frameworks for that. You wouldn't get the performance which you need out of scikit-learn. Okay, so this is the website. One of the things which might be interesting to know is that Intel in its one API framework, let's say, also has a Python distribution. With it, they ship NumPy, but also scikit-learn, and it has some optimizations. So that's interesting to know, since typically their distribution is going to run a bit or quite a bit faster than whatever you can get from the default repository. Intel is kind enough to contribute back into the main repository, but if you want the latest and the greatest, then it might be worth to base your software stack on Intel's Python distribution. Okay. Machine learning tasks. So as I already mentioned, supervised learning and regression and classification. Unsupervised learning, it can do clustering. So this is specifically for scikit-learn, by the way. So we will work with a data set, and that's kind of a running example for everything we do in this particular for this particular part of the training, and that's the World Happiness Index. So that is an index which is published yearly for almost 10 years now, or even longer. I don't quite know when they started. So I'm going to use two particular years, two publishing years of that index, 2015 and 2016. Data is publicly available. It is also in the repository itself, just for my and your convenience. I'm going to use 2015 as a training set and 2016 as a test set. All right. That means, of course, that I'm not going to use the 2016 data during training, only for testing when I'm done. Think I have the best model, then see how it works on unseen data. So what is it actually? Well, the happiness score of a country is just a number. I think it's between 0 and 10. I'm not entirely sure. It doesn't really matter. So it's based on the number of indicators. So it has to do with the economics of country. it has to do with the family situation, it has to do with healthcare, with freedom, with trust, and that specifically means trust in government, trust in enterprise, and so on. It also may have something to do with generosity. How do you contribute to social causes? And there is also a dystopian residual. So essentially, of course, how do you measure economic factors? Well, for each of these categories, actually, they take a particular proxy. So a particular number, which they can use in order to kind of approximate, to have a proxy for that particular category of things that contribute to the overall happiness of the population. So for the economy, that is just the GDP, gross domestic product. For the family situation, that's the size of your social network. For healthcare is your life expectancy, and so on and so on. So for each of these categories, they have a number that is based on some observations, some measurements in that country. Okay. So all of that is, of course, quantitative data. So those are numbers. And there's also a geographic region, and that, of course, is categorical data. So the geographic regions are pretty broad. So you've got Western Europe, Southern Europe, East Asia, Southern Asia, and so on and so on. That is categorical data. So that's nice because that same data set gives us both quantitative and categorical data. And that's an interesting mix, both in terms of training data and of course in terms of tasks, because we can do regression to predict one of the, or to predict the happiness score, for instance, or we can do what's it called? Regression and the other thing, sorry, predict categorical data, so classification, yeah, there's the word, classification on the region. Okay, so what does it look like in practice? First thing you do, of course, is data visualization, and then everything that's green is kind of happy. Everything that is yellowish, brownish is getting unhappy. So probably not that many surprises. In the Americas, essentially the Canadians, and this is either Costa Rica or Panama, I think it's Costa Rica, are two very happy countries, while the United States and Brazil are, and also Chile, Argentina are reasonably happy. In Europe, there are also a few surprises. The Scandinavian countries are very happy. Norway and Iceland, I also think, is extremely happy. Belgium, I can't quite see it, but I think kind of okayish. And then, of course, you have some countries typically where there is a war going on, and those are either unhappy or extremely unhappy, or where the economic situation is, let's say, unbalanced, like for instance India. There, yeah, you have a lot of, let's put it that way, that the standard deviation is pretty large. And let's phrase it like that. Okay, so first task, we are given quite a number of things. So we are given actually all the data, essentially. And what we need to predict is the happiness score. Okay, so the data is on the one hand numeric, so quantitative, and on the other hand, only for the region we have a category. So that's of course a regression task. We try to predict a number, in this case a single number. So first step is always have a look at your data, and a good way to do that is load that into a pandas data frame and use Describe, because that's going to give you some crude statistical measures about your data. That's always a good way to start, because one of the things to have a look at is the count here. And one of the things that you see is that the count is equal for all these values. And that's great because that actually means that we are not dealing with missing data. That's good. So that's the first thing to check. If you notice different numbers in columns, then you have missing data. That's for sure. And then you need to do something. What you need to do is up to you, but you need to do something. Okay. Then the other things to look at are, for instance, the maximum and the minimum. So the happiness rank, obviously, yeah, that's an integer. I mean, it's 1, 2, 3, 5, etc., etc. So that's not very surprising. The happiness score, as you can see, ranges from 2.83 and goes up to 7.6, let's say. And then we see other measures and so on. And one of the things which you notice, and which is why this kind of thing is useful for, is that there are some of these numerical measures that have a maximum that is significantly larger than others. For instance, the GDP per capita goes up to 1.7, while on the other hand, the trust actually goes only up to 0.55. So yeah, the different features, because each of these columns now represents a feature of a certain country, range between different values. So that's a bit of a red flag. We should probably normalize the data, scale the data. Okay, we need rescaling. Okay, so we already know that there is no missing data. Another way to check this perhaps a bit more concisely is just use the info method on the pandas data frame, and then you see that indeed each column actually has 158 entries. So we have data in 158 countries. Okay, that is a smallish data set, by the way. So essentially that means that something like deep learning is maybe not your best guess. We need an algorithm that is simpler, has less parameters because we don't have that much data, but that can discriminate sufficiently, that has sufficient expressive power in order to describe our data set. Okay, so we have no missing values, that's good. Otherwise, we can use an imputer. Okay, so we need to extract the data. That's the first part of our pipeline. So basically, we are going to set up such a pipeline that automatically ingests our data, deals with missing data, if necessary, checks for outliers, which we're not going to do here, and which will transform our data, which we'll definitely do here. Okay. So the easiest way to do that is, in this case, to read the data into pandas data frame and then extract columns from that data frame. Okay, so the transformation is basically scaling numerical values, and then we need to do something with the regions. Because what are we going to do with the regions? The regions are not numbers. The regions are just strings, labels at the end of the day. So what are we going to do with them? Dependent variables. So basically, yes, the happiness score is computed from the other variables. And the happiness rank is just the ranking which you get when you sort the countries by happiness score. So the country with the highest happiness score has the highest rank. It will have rank 1. The country with the lowest happiness score will have rank 158. I hope that kind of answers your question. Okay. So basically, we will have to scale numerical features, and we'll have to do something with our regions, because those are labels, strings, and of course, an algorithm can't do much with that. So that's not interesting. So somehow we have to go to a numerical representation of our regions. Now, one of the things which we could do is something very simple. We could say that I don't know, North America gets label 0, that South America gets label 1, that Europe gets label 3, that Africa gets label 4. I'm just going from upper left to lower bottom. There is no other order involved here. So basically, I can assign a number, consecutive number, to each of the regions until I'm done. Okay, I could do that. However, that has a drawback, and that is that if I just represent those numbers as input to my model, given how many models work, that would implicitly define an order on those regions, because 1 happens to be larger than 0, and 5 happens to be larger than 3. So that implies something that actually isn't there. That order shouldn't be there. So that's maybe not your best way to represent categorical data. So another way to do that is to use a one-hot encoding. We'll see what it is in a minute. So let's first have a look at numerical attributes. So we define a pipeline for that. Okay, so we import from sklearn compose, and we have a column transformer. And from preprocessing, we get a min-max scalar. Okay, so we have a list. We get our columns, all our column names, and the 5 up to 13, not including, basically means, okay, I know where my columns are, I had a look, and these are my relevant columns. Those contain the numerical data. So only the input. The happiness score is not here. This is just for the input. Okay. And then we define a transformer. So we have a column transformer first. So that is going to act upon data that is in a column. Makes sense. And what is it going to do? It is going to call a min-max scalar. Okay. And it's going to do that on all these columns here. Okay. And the name of that transformation is going to be minimax. Okay. So this is just a string I can choose. That is in order to get feedback while my pipeline is running. If something goes wrong, this minimax string will also be printed as the component in my pipeline where things go south. So that is something that you use for your own convenience. It has no impact on how this runs. Okay, so what's the min-max scalar going to do? Well, it depends a little bit. You can run the thing in 2 modes. You can run it in fit and transform, or in transform only. Okay, so I'll come back to that in more detail later. Okay, so for the categorical attributes, we need to do something different. So we create a different pipeline, a second pipeline, and basically we need to extract it. And then we want a one-hot encoding. So basically for Belgium, it happens to be in Western Europe, Canada happens to be in North America, and so on. So we can represent this data in a different way. We can say, okay, rather than having one region column, we're going to have a column per region. And that column is either going to contain a 1 or a 0. And pretty obviously, in this particular case at least, since each country has just a single region, it means that only one of those new columns is going to contain a 1, and all the other columns are going to contain zeros. So that's why it's called a one-hot encoding. Only one bit out of this bit representation is going to is going to be a 1, because the label is unique for a country. Okay, so of course, this means that if we have many regions, if we have many different region names, that actually we will have quite a lot more columns in our data set than we started with. That's a price you pay. Okay, how do we do that? Again, we have a column transformer, but in this case, the operation which we are going to do is a one-hot encoder. And as you can see, that happens here. And I can either specify my own set of categories if I know, or I can just use auto. Okay, this is already interesting, but let's continue. So now, of course, what we want to do is, or what would be annoying, is if we would have to run our numeric pipeline and our categorical pipeline separately. We don't want to do that, so we want to create a single pipeline for the whole data set. And this we can do using a feature union component. And that actually allows us to run two pipelines in parallel. They will act on different columns, and they will be in parallel. So within parallel, in this particular case, I don't necessarily mean that they run at the same time. Just that conceptually, the data flow is such that they actually can be thought of as running in parallel. Whether they run in parallel or not depends on the implementation. But conceptually, this can be done in parallel, and you should think of it that way, at least conceptually. Okay, so the feature union pipeline actually contains two components, our categorical pipeline, so the region attributes, and the numerical attributes here. Okay, so as you can see, it's quite easy to combine multiple pipeline components into a network that is the final pipeline. So maybe let me backtrack just a second. So here, coincidentally, both for my region transformer and also for the numeric attributes transformer, there was just a single thing to do. So for the numerical attributes, that was that min-max scalar. For the numerical data, it was just a one-hot encoder. Suppose that you want multiple pipeline components, multiple transformers, one after the other. It's very easy because you've probably noticed that this is a list. So in a column transformer, each component in that list is going to be executed one after the other. So in this case, we would first have a one-hot encoder, potentially followed by a second transformer, followed by a third transformer, and so on. So this would form a pipeline in series, while our feature union is going to branch. So basically, that's going to encode two parallel pipelines. So as you can see, this gives you full freedom of designing pipelines that potentially can be quite sophisticated. Okay, so once we're done, then we have our preparation pipeline. That's the end result. And basically, we run the fit transform method on that based on our input data. And this is quite important. This is the fit transform. So the result is going to be a NumPy array. So if you're into machine learning with Python, it's very useful to know a little bit about pandas, about some plotting library, but also about NumPy, because lots of things are done in with those packages. Okay, so now we're done in the sense that we're ready to start training. Okay, so the first thing we need to do is we need to create our learning algorithm. Okay, and in this particular case, I'm going to choose rich regression. So that's just rich in this particular case, that's the name. And it has two parameters. It has a parameter alpha and the parameter fit intercept. Okay, so those things are in fact hyperparameters. Without any doubt, you've heard the term hyperparameters. So those are parameters of your algorithm that are not changed by the training. So these are things which you specify up front. They're fixed during the training algorithm, so they don't change. So that's why they're called hyperparameters, in contrast to all other parameters that are being modified by the training process. Okay. And then we do the training. So basically I get my input. This I already have. That's my training data. I represent that by X. And I've got my Y. And I get that out of my input data just by creating a NumPy array. And then I use rich regression fit XY. Okay. I should stop here and ask you what's wrong. Something is not okay. I've been talking about methodology. So with respect to methodology, something is quite fishy here. What would that be? Hint, it's got to do with pipelines. What I'm doing wrong here, validation set. Yes, I don't have a validation set yet. So that is indeed something that I should consider as well. But in this particular case, I'm not going to need a validation set in the sense that for rich regression, I'm just going to do the fitting. There is no yardstick in that algorithm. So I will need a test set, but I have a test set. This is a 2016 data set, so that's fine. But there is something else with respect to my pipeline. I've gone through quite some effort to have a nice formal pipeline for my input data. And now for my output data, I just do something stupid. Outside of the pipeline framework of scikit-learn, I should actually get my output out of my data also using a pipeline. Because it might be that I also have to transform my output as well. For instance, I could decide that given that the range of the happiness score is between, what was it, 2.7 and 7.6, something like that, that I actually prefer output between 0 and 1. So I'd have to normalize my output data. Okay, I'm not doing it here, but if I just ad hoc suddenly fetch my data using some dubious NumPy plus pandas thing, rather than a principled approach using my nice scikit-learn pipelines, actually I'm asking for trouble. Because what I want to achieve at the end of the day is, of course, that I have something that is consistent and that I can run front to end without having to think about it. So this violates that principle. So that is not really a good idea. Okay. Then, of course, that is the problem. That's why the question marks are there. So that is one of the things, and I should really warn you about that. There are quite a number of things in these slides that are on purpose wrong for some reason in order to make a point and to be able to ask you questions about it. And there are usually only subtly indicated. So if you just go through the slides, then of course you would ask yourself, okay, why is the question mark here? It's not explained on the slides. So sorry, that's how I make slides. Slides are there to support a story. They're not intended as standalone study material. I don't believe in standalone slides, well, in slides as standalone study material. I don't think that works. Okay, so just to draw your attention to that, remember this because it will happen a couple of times. There was someone who raised his hand, so if you have a question that you can't put in the chat, feel free to activate your microphone.
Hi, sorry, can you hear me?
Yeah, just let me fiddle a little bit with the volume. Yeah, go ahead.
So my question is related actually to the output. So I'm thinking of a scenario where you in the pipeline of the input, you throw away some outliers, for instance, and then you have to do the same for the output, right? So there need to be some sort of association between both, but I don't see it here.
Yeah, so basically there is no filtering step here. So if you want a filtering step, then of course that should be a transformer which applies to all the columns in your data set, or more specifically to all pipelines, all sub-pipelines up to the point where you want to do the filtering to get that consistent. Absolutely. So that is also why this is dangerous, what I'm doing now, because indeed, suppose that I notice, yeah, okay, there are outliers, okay, I need to deal with them, and I would do that in my input pipeline, then I would be in deep trouble if I forget about the output pipeline. So what I should do in that case is create an input pipeline, okay, did that, ready. Create an output pipeline, didn't do that, okay, we'll do it, and then add an additional pipeline component that does, for instance, that does the filtering to eliminate outliers. So that would be the way to deal with that. Does that answer your question? Okay. So you have to think of this pipeline as a network, and what should come out of the network is something consistent. So that is, of course, determined by the flow through your pipeline. So that should make sense for what you want to get out of it. Meanwhile, there was someone else raising his hand, I think. So again, feel free to activate your microphone if you have a question. Not really, I think. Okay. Yeah, so there seems to be.
Yes, sorry, I couldn't find the right button to click.
No
So
worries.
I'm a little bit concerned about this outlier filtering in the output pipeline, because so far what I have learned is that outliers could either be errors, so you have to filter them out, but they could also mean the discovery of a lifetime, because sometimes outliers could mean that, you know, something very special is going on here, and we want to know what special things are going on. So if you are going to filter them in the output pipeline, you're not going to make those discoveries. So I think outliers are something that we have to think about in the input pipeline and not in the output pipeline. So
but there is no, just to avoid the confusion, there is no such thing as an input pipeline or an output pipeline when you're talking about outliers. If you're talking about outliers, you always consider input and output simultaneously. Okay, that's one part of an answer to a question. The other part of the answer to a question, to your question, is I did not say that you should eliminate outliers. What I said is, if you want to eliminate outliers, so this is a matter of choice, and that choice, as you indicate very correctly, critically depends on what you're doing. What's the nature of your outliers? So for instance, if I'm looking at a production process and I measure in Kelvin, let's say a negative temperature, I'm 100% sure, based on physics, that that is an outlier which I should eliminate, or at least which I should investigate but not take into account for my machine learning project. On the other hand, and that was the other example, suppose that you are doing CFD and the big majority of your data set consists of flows that are non-turbulent, but some of your measurements are in a regime where you start to see turbulence, just a bit. Is that an outlier? Maybe not. But it depends. It might be that those points shouldn't be there from not from a physical point of view, but from a processing point of view, that the fact that there is turbulence is course, your process parameters are not really what you want them to be, because you actually want laminar flow or something like that. But essentially, then it means that if you are trying to learn the process parameter, that you should take them into account, because if you start getting into a turbulent regime, you want to dial back some numbers so that you get back into a regime which you want to have. So I have never said, and I will never say, that you should eliminate outliers. What I do say is you should consider outliers. What you do with them depends on your problem. And it's the same with missing data. You can deal with missing data in many ways. One of the ways to deal with missing data, which is quite simple, is if one feature is missing, eliminate the whole data point, everything, from your data set. Don't do imputation. That's the simplest approach. Is that the right approach? That's a different matter. You can make a different choice. You can say, okay, if I miss one particular feature, I'm going to take the average between the previous and the next value. Is that okay? Maybe. I don't know. Depends on your problem. You can say, okay, if a value is missing, I'm going to replace it by 0. Is that okay? Maybe. Maybe not. I don't know. It depends on the problem. So how you, what you do with outliers, what you do with missing data, is something that is really very problem dependent. And there is no way that anyone should say, okay, you should do this with missing data. You should do that with outliers. Because it depends critically on what you're doing. So without context, there is no meaningful answer to that. And that is actually what I said, but apparently I didn't say it clearly enough. So I'm guessing that answers your question. If not,
No,
let me know.
it wasn't actually a comment on what you were telling us. It was more of an addendum to Ahmed's question.
Yeah. So you're perfectly right in this, but I should have stressed it more. So basically, that is indeed your, as I already said, your remark is very much to the point. There is no absolutes in machine learning on how you need to deal with data. The only absolute there is that the way you deal with data must be consistent. That's the important part, and that's the advantage of these pipelines, that you can make that consistent and reproducible. So that's the idea here. Okay. All right. So we did our training. That was easy. That was just applying the fit method. We're done. And then we can start doing regression. So basically, then we use the predict method on some input, and we see what we get back. Very easy. Okay. So how do we assess how well we are doing? So basically, what you can do, if you have a trained model, in this case our rich regression model, we can apply the score function, and that would give us the training error essentially, because x and y, remember, are our training input and output respectively. And in this case, we get 0.9984. So this is a very high score. It goes up to 1, so this is a very good score. So we can be quite confident that this is a good training. Maybe. Because of course this is on the training set, and yeah, well, okay. What you can also do is, rather than use the entire data set for scoring, is to use cross-validation. And then of course we use the model, and we are going to split the data set into various parts. Some of them which we're going to use for training, others which we're going to use for validation. Well, one other which we're going to use for validation. In this case, we are going to split the data set into 10 parts for cross-validation. And what we're going to use is the negative mean square error. So basically, and then we don't want the negative number, we don't want the square, we just want the square root of that. And then you see that we get values which are fairly low, which is okay. there is a 20% there, not that good, but all the others are below 10%, so this should be a low number, so this is kind of okay-ish. So yeah, seems quite well. Now, another thing which you might have had some questions about was, okay, I defined my algorithm, the rich regression, and I said, yeah, I've got alpha, it's circle 5, and I've got, what was it, fit intercept, and I set that, I think, to true, if memory serves. So based on what? This is a hyperparameter. How do I know what the alpha value should be? How should I know whether I need to use fit intercept or not? Now, of course, rich regression is fairly simple, straightforward algorithm. So it's very easy to just go to the literature if you don't know the algorithm and just check, okay, what's it doing? And what's the semantics of alpha and fit intercept? And based on that, make an informed choice. In this particular case, we have two hyperparameters, alpha and fit intercept, so that's easy. On the other hand, if you have a deep neural network, as we'll see later on, you have many more hyperparameters. How are you going to choose those? So one of the things you can do is investigate what the influence of these hyperparameters is on the outcomes. And that's hyperparameter tuning, essentially. And this is something that we can do. So we define a grid of parameters. So that's basically a dictionary that consists of the name of the parameter and the list of the values we want to consider. So for a Boolean value, that's pretty simple. That's true or false. For numerical values, you choose some range. Okay. So then we do a grid search with cross-validation. And basically that means that we're going to do this training algorithm many times, once for each instance of our hyperparameters, and of course a number of times, 10 times, for cross-validation. Okay. So if we do that, and that's very easy, again, we have our algorithm, and then we use the fit method. Note that this fit thing occurs many times, so that's one of the things that I appreciate quite a lot with respect to scikit-learn. It's very nice because naming and such is very consistent, so that is very nice. Relative size of the validation set, again, it depends. What I typically do if I really have a validation set that I set apart is make it as large as possible. That also goes for the test set, by the way. I try to make it as large as possible, but it's always a compromise between, on the one hand, the size of the data sets which you have available for training, which should be enough to estimate your parameters. Otherwise, you are going to overfit, so that is unpleasant. And the on the other hand, you also need sufficient validation data, test data. So if possible, I'll split between test and training 50-50. And then the validation set, usually I stick to something like 2/3 if I can get away with it. Sorry, 1/3 if I can get away with it, or 20%, something like that, depending on what I can do. So sensitivity analysis and fine-tuning are indeed sort of related. So if I just use this approach here, so with the grid search CV algorithm, I'll just get the best value. So in that respect, it's a search algorithm rather than a sensitivity analysis. With a sensitivity analysis, you would look at trends. If you change the alpha value, you would see how it would influence the outcome of your training quantitatively. While just a search algorithm will just give me the best values for alpha and for fit intercept, period, nothing more. So it's related, yes, but it's not the same thing. But the purpose is similar in a way. A sensitivity analysis is, of course, a bit more intelligent than just a brute force search. Okay, so I can get the best parameters, and in this case, that would be alpha is equal to 0.0005 and fit intercept is equal to true. Okay, again, let me hold for a second and ask you whether you're happy with this. Given that I asked the question, it means I'm unhappy at this point. Yeah, indeed. So basically what I get as the result is the lowest value I specified for alpha. I would have been equally unhappy if the result would have been alpha is equal to 0.5. So basically I'm on the edge of my search space. And that might mean, if I'm lucky, that it is the correct result. Hooray, hooray. But on the other hand, it might also mean that the actual alpha value, which is optimal, is lower, is outside of the domain I'm considering. So this is a bit of a red flag. However, let's go with it for now. Okay, so this is the training result. And basically there are two curves here. There's the blue curve and the orange curve. So essentially the blue curve is just happiness rank. And of course, the way to get that is very easy. You just predict for each country, you predict the score, and then you just rank them. It's easy. And basically, as you can see, the blue curve obviously is monotonic, of course, because that is the target. That was in my CSV file. And the the orange curve is not monotonic. So basically that means that these countries here are not in order. So they should have been swapped. Each time you have such a peak and a valley, it means that that countries should have been swapped. But as you can see, overall, this is pretty good. Okay. So the training has done quite a reasonable job. Okay, but of course, the proof of the pudding, etc., is in the eating. So we actually need to test our model. And then, of course, we need to get our testing data. And that was in a different pandas data frame, the 2016 data set. And now notice the difference. When I ran my pipeline for the training data, you might have forgotten, but there was a fit transform here. And now I just run transform. Okay. Any ideas why I'm doing this? Why am I treating my test data differently than I treated my input data? That's a little bit bizarre at first glance. Why don't I just use fit transform here? Obviously, the name is the clue. The fit actually means that the parameters of my pipeline are going to be trained. Wait a second, parameters in pipeline. Well, there were actually two parameters in the pipeline I defined, or actually three if you want to be very precise. So let's backtrack and try to remember what a pipeline did. So there were two components. One component was the one for numerical data. The other component was the one for the categorical data. Okay, so in the pipeline for my numerical data, I had a min-max scaler. So the intention of the min-max scaler was to ensure that each feature, each numerical feature, was scaled from whatever its values were to something between 0 and 1. And that's just a linear scaling. So that means that for each feature, I need two numbers to do this linear scaling. And that was part of running the pipeline on the training data. So the pipeline would have a look at each individual feature, make a note of its minimum and maximum value, then recompute all the values taking into account its minimum and maximum values, mapping the minimum to 0 and the maximum to 1, and all the rest in between in a linear fashion. So that requires 2 parameters per numerical feature. So I set first 2 and 3, and yeah, actually it's more. It's 2 times the number of numerical features plus 1. Okay, so that is a parameter. That has been part of my training. So that means that if my test data contains data that is outside of that min-max interval, which I determined by training, that I should not modify my pipeline accordingly, because that would be cheating. So, of course, if my test data contains a significant amount of data that is not, well, that is being transformed into negative numbers or numbers that are larger than 1, then I have a problem, because then my test set and my training set are distinct. They don't represent the same data. Okay, so the underlying assumption here is that my test data and my training data are in fact representative of one another. They should be kind of interchangeable. If that's not the case, I have a problem. I have a methodological problem. But at any rate, what I should do is to modify the min-max parameters, for instance, in this, when I run this pipeline, because that would be using the test data in order to modify the training. Not the rich regression algorithm, but my data pipeline, which is part of the which was part of the training process. And these parameters have been learned. So if I allow them to be modified by the test data, my training will be influenced by the test data, and that's what I definitely should avoid. So that's why this is very important to run the pipeline with transform only and not with fit transform when you're dealing with test data. Okay. So basically, then you can do prediction, and you can compare that to the output which you want. We can do the score, and then you see that we still get something very nice. So 0.995, which is very impressive given that the maximum is 1. So that again looks good. On the test data, this does quite well. And indeed, that is what you see. If you look at the target, again, that's a monotonically decreasing function. The result of rich regression, as you can see, fits that reasonably well. Okay, I notice one thing. What do you notice? Yeah, exactly. Underestimation. So basically, my predicted values are more or less consistently below the blue line. So essentially, there is some drift in my data. So that essentially means that the happiness actually changed. So the overall happiness in the world just went up a little bit. So in 2016, on average, the world population was a bit more happy than the year before. Although that is very comforting news, I mean, that means progress, that's great. It also means that actually my training data set was not representative for the problem. And I should have made a different split between my test and my data, my training and my data set. Methodological problem. So this is drift in data, where you actually have data that changes as a function of time. And that, of course, is a very regular occurrence. And that is also something that you would see in practice. So it's something to take into account, that sometimes your, let's call it, your problem changes, whatever it is, your process changes, there is drift on it. And that might mean that on a regular basis, you have to retrain your model based on current information. So that is important to keep in mind, that once the model is trained, it's not necessarily carved in stone. You might have to revisit it later in view of changing circumstances. Okay, let's pause here for a break, because that seems like a good time. Well, we're already late for a break, but nevertheless. So let's break for, say, 10 minutes. So till, what is it? 11:10. If there are any questions, feel free to put them in the chat. And feel free to help yourself to coffee, tea, or any beverage of your choice. Meanwhile, I'm going to do some administration.
Dat is een heel lekker grond. Dat is precies. Heb je dat gezien? Ja. Nou ja, dat is dat. Ik heb niks aan doen tot ik tegen u gezegd had. En die was het niet, maar ik ja. Nee, dat weet je dat gezien. Ik heb gekeken en gekeken, maar wat er komt. Ik kan dan naar venster zo naar beneden, maar ja, dan pik ik het. Het is waar. Ja. Kun je mij niet zeggen waar ik moet doen? Ja, ik zeg wel. Ja.
Okay, let's continue. I'll share my screen again. Okay. And there is one comment in the chat. Let me have a look what that is. Yeah, it is indeed possible that some things in the repository are slightly outdated. I did a pass over everything somewhere last year. I didn't do that this year, so indeed it might be that something is now outdated. And I think I remember something with auto or something, that there was something with that which might change in future or something. So yeah, I'll have to have a look what's going on now. Yeah, I'll have to see. I can't tell you at the moment what it might be. But yes, it could be that there is some changes in the Scikit API, and that is not taken into account in the notebooks yet. It is also possible that I forgot to update some things in the hands-on repositories. So please consider source code as ground truth and hands-on as something that may not be entirely up to date. Because as you can guess, it's a bit annoying to keep 3 notebooks or 3 versions of every notebook in sync. And so it might be that, yeah, that's a manual thing. So it might be that I forgot to update something as well in these hands-on notebooks. So the source code was certainly checked completely last year. And normally with scikit-learn, changes are not that frequent. So I would expect that to be okay. Nevertheless, it can be that some things are out of date. That is entirely possible. Okay. Thanks for pointing it out. I'll have a look at any rate. Okay, let's continue. So, task number 1 was regression. We tried to predict the and we were reasonably successful. However, there is one thing which I still want to point, well, two things which I still want to point out. One thing which I forgot, and the other which is also quite important. So one thing I forgot to mention is the other parameter during the training was indeed the detection, the automatic detection of labels for the classification. So that also means that if my training set would, for whatever reason, miss a particular region, or the names of those regions would modify, or an additional region would be included, or something like that, that of course, given that I only do a transform when I read my test data, and also of course when I do my production runs, that would also give rise to errors. So that's something that you also need to take into account. Then the other thing essentially has to do with the cross-validation thing. Sorry, the hyperparameter tuning, which we did. So as you recall, we actually got 0.005. And I said, okay, I'm suspicious about that, and many of you agreed. And of course, you're perfectly right. Now, there is a very fundamental reason for that. And that is that if you take a closer look at your data set, well, at this particular data set, this is, of course, a very artificial data set. And if you look at it and see how it is actually created, then you will see that the happiness score is in fact just a linear combination of all those features, except for the region. So basically, this is just a linear model. Now, if you think about what ridge regression is, if you look at it, you will see that it is linear regression with a regularization term. That regularization term ensures that the weights for the linear regression don't get too large. So it's basically just the square, the sum of the squares of all these weights, these linear weights. And that term is multiplied by alpha. So alpha equal to 0 simply means that our ridge regression model is a simple linear regression. And that is exactly what we actually would expect, knowing that in the first place, the World Happiness Score is computed linearly as a linear model from all those numerical factors which I talked about. So that is something to keep in mind. So essentially, it means that our model, in this case, the ridge regression, is a bit too powerful to describe our actual data. But of course, you can't know that upfront. It's easy to come to that conclusion when you know how your data was generated, which in general, of course, you don't know, because if you know how your data was generated, then probably you don't need machine learning. Or if that was extremely slow and inference in machine learning is faster than your computation process, that's a different discussion again. That's what I mentioned with the quantum chemistry and the potentials which are computed through machine learning, or ab initio, where ab initio is quite slow and machine learning is quite fast and gives you reasonable performance in terms of quality. Okay, so that were a few remarks. So now we turn to a different task, which is classification. So again, we're given all the numerical attributes, not the happiness score, but apart from that, everything that's numerical. And what we want to predict is whether a country is in Western Europe or not. Okay, I could have done something more general. I could have said, well, okay, predict the region, rather than just whether it's in Western Europe or not. So it's probably quite obvious why I chose to do this rather than predicting all the regions. Well, we only have 158 data points. So that's a very small data set. So predicting everything, all the regions, is going to be a bit hard. Just doing a yes-no classification is maybe feasible. Okay, so that's a classification task. And again, we have data preparation. So the numerical pipeline is exactly the same as in task 1, no problem. And then we add a new column. Note that again, we are doing that in a very unstructured way, in a very unsystematic way. So no, don't do that, use a pipeline. And basically, that is going to be our output. Okay, so of course we need a different algorithm because rich regression by its name only does regression. So if we want to do classification, we have many options. And in this case, we're going to use Gaussian naive Bayes. So Gaussian NB, the NB is for naive Bayes. Okay, we instantiate our algorithm. Hooray, no hyperparameters, that's good. Okay, so of course, the Gaussian in the name implies that there is an assumption. This algorithm is designed to deal with data, features, values that are Gaussian distributed, so that have a normal distribution. Is that the case? Maybe, maybe not. So that's one of the things which you also have to consider when picking an algorithm. Are the assumptions the algorithm makes on the input values, are they satisfied by your data? If not, you might have to choose a different algorithm. So in this case, I didn't bother to check, but of course you should check whether that assumption holds that your input data, each of the features, is normally distributed. Okay, so we are going to train as usual, just with a fit, no problem. And notice again we have input output, so no problem. We do the scoring, okay, and we get 93%. So that's not as good as before for our regression problem, but it's still quite reasonable. 90%, 94% almost accuracy. Oh, not that bad. Okay, so let's test the model. And again, of course, we use the pipeline. And that's the same as before. We do a prediction and we do the scoring. And we end up with 86%, more not to write home about, but also not particularly bad. So looks reasonably well. So not so good, but who knows. So one of the things which you can do in order to assess the quality of a classification model is compute the confusion matrix. And the confusion matrix just tells you how many categories, how many data items are predicted correctly for a certain category, and from other categories, how many are wrongly predicted for that particular category. So this would be the confusion matrix. In this case, it's just a 2x2 matrix since we only have one feature, which can be yes or no. Well, one class that can be yes or no. So basically, we have in total, we have 132 countries which are classified as not in Western Europe. And so these are the false positives and these are the false negatives. So that's basically the idea. So a false positive means the algorithm says it's in Western Europe, while actually it's not in Western Europe. The false negatives means it should be in Western Europe, but it's predicted not to be in Western Europe, but it is actually in Western Europe. Okay, so that does not look well, because if we have 17 countries that should be predicted to be in Western Europe and are not, then we actually have a problem. That would be a rather massive Brexit operation. So basically, something is rotten in the Kingdom of Denmark, regardless whether Denmark is in Western Europe or not, according to the algorithm. So something is wrong here. Now, one of the things that you typically do when you consider a data set for classification is having a look at how many members do you have per category. And then, as you can see, this is just a simple plot with the count for each region. And then you see that for Western Europe, if I can find it, where is Western Europe? Here. Actually, that we get something like 20 something countries, but this seems reasonable. I mean, there are, of course, yeah, there are some outliers, like Middle East has few countries. Of course, there are few countries in Central and Eastern Europe, and so on. Australia and New Zealand are few, but basically, of course, it's a reasonable distribution until you realize that actually we're asking a yes/no question. And then, of course, there are very many countries that are not in Western Europe and only a few that are in Western Europe. So our data set is very skewed. We have very many examples that are for not in Western Europe and very few for in Western Europe. So from a very pragmatic point of view, the algorithm can do a very simple thing. It can predict for almost everything, for every country, that it is in Western Europe, that it is not in Western Europe, and it will be right in most of the cases. And you can even do the computation. We have 158 countries in total. We have some 20 plus countries in Western Europe. So let's round that to 160 and 20. Okay, basically, if I say that no country is in Western Europe at all, then I would end up with an accuracy of 140 divided by 160. So 7 in 8, which is approximately our 80-something%, which we actually got. So basically, the problem is not as such with the algorithm, but rather with our sampling method. So basically, we have very biased data. We have data that is distributed in a very strange way, and we should take that into account while sampling. So one of the things we could do in this case is stratified sampling. So basically making sure that the distribution is augmented with sufficient examples from Western Europe. Okay, so basically that's something that you need to take into account when you're doing classification. How is the distribution of your classes? If you have a class with very few examples, the likelihood that you're going to manage to do a good prediction on that is smallish. Okay, unless you have a very large amount of data. Okay, let's turn to third task, which is essentially clustering. So this is unsupervised now, and we are given basically everything that is numerical, except again for the happiness score itself. Okay, and we want to find countries that are close, and in this case close. What I would like to end up with semantically is in fact 3 clusters. Countries that are nice to live in, countries that are okay to live in, and countries that I prefer not to live in. Okay, so I'm going to do clustering, and I'm going to choose the number of clusters equal to 3. So that is, in fact, a hyperparameter. So basically, it means that I have to fix that in advance with k-means clustering at least, because the k in our case is going to be 3. So there are different clustering algorithms which try to figure out somehow which number of clusters is optimal. Whether that's successful or not depends on your problem, and for some things this might work, for other things it may work, let's put it that way, less well. Okay, so how does k-means clustering work? You just choose k seeding points, so essentially your data points. And then you start assigning each point to the nearest mean value. Okay, so basically, in case of 2 clusters, I'll do it that way. So this is a seed point here, the blue one, or the green one, don't know what color that is. And here the red one is another seed point. And so basically you choose you assign it to a cluster based on the distance between the data point and the seed point. Okay. And then you recompute the mean values. So basically that means now we will compute the center of mass of all these points here. That would be somewhere here most likely. And we do the same there. Then we would add probably somewhere here. And we repeat until we're happy, until we have some convergence. So that would be the second step. And you can keep on that until keep on going until there is no more change. So that would be a very simple implementation of the k-means algorithm. Okay. So data preparation and training is very similar as before, same thing. And essentially, we create a new algorithm, k-means, and that has one hyperparameter, which is the number of clusters. Given what I want as a result, in this case, I can choose n equal to 3. Whether I will get what I want is a different matter. I don't know that upfront. And in general, it's not trivial to say how many clusters you need to find. You don't know, because that's one of the things you do. You're trying to find structure in data without any further information. So what you will get out can't predict in advance. So that's a matter of then looking at the result and trying to make sense of that. And there may be sense in it or not. We'll see. Okay. So the training again is quite simple, but now of course the fit algorithm takes just a single parameter. There is no output. This is unsupervised learning. Okay. So for convenience, we're going to add a cluster label to the data set. Again, you're just filling a little bit in the pandas data frame. And basically, we will examine the clusters. So in this case, we'll do a box plot by cluster for all the columns. Okay, so this is each feature. Each box plot represents a single cluster. And then you see that indeed we get something interesting. So the third cluster here has scores quite high on economy. It also scores quite high on family, on health, and so on and so on. So for most of the indicators, it actually scores quite highly. While the first cluster here scores a bit less than the third, but somewhat significant, well, sometimes significantly better, sometimes somewhat better than the other ones. Okay, so it might actually be that what I wanted to get out of this, a cluster of countries I definitely want to live in, and a cluster of countries I definitely don't want to live in, or prefer not to live in, depending on how strong you want to put that, might actually be the result of this unsupervised clustering algorithm. Okay, so looks interesting. It also, of course, gives you some insight, because if that would be true with respect to the countries, then basically you see that GDP, so economy, is quite important. Family also seems quite important, and so does health. While on the other hand, freedom is somewhat less pronounced, let's say, and things like generosity hardly seem to play a role. So this clustering algorithm also gives you perhaps some insight in what makes a country nice to live in. Perhaps, maybe not. That is indeed true, obviously. Not all of these things are independent. That's quite correct. So indeed, if you have a higher standard of living in terms of GDP, it means that there's significant money in order to make sure that there is good public health service. So that's one thing. On the other hand, there are counterexamples. For instance, countries like Cuba, countries like Turkmenistan actually have a fairly low GDP if you look at the real GDP that people get into their hands. However, the health system is quite good. So, and we will actually see an example of that if we look at the cluster in detail. But in general, yes, absolutely, you are right in that respect. Yeah, absolutely. That is perfectly true for Cuba, at least, and also for other countries. So, yeah, the government pays those people, but the wealth and hence the GDP is not distributed accordingly. So it's a bit, yeah, depends on how you interpret the numbers. Okay, so basically, one of the things which in such a case you should also consider is how many countries do we have in each cluster? Because if we have a very small cluster or a very big one, then yeah, maybe our clustering algorithm did not do such a good job. But as you can see, that is quite reasonable. Indeed, the third cluster is the smallest one. It has 31 countries in it, but it's not an order of magnitude less than, for instance, cluster the first or the second cluster. So based on these numbers, I'd say this could be okay. It's not a red flag, but it's something that you need to check. Okay, so the winners are, I'm going to look only at the category, at the cluster, which I suspect to be the countries I want to live in, just out of political reasons, essentially. It's not nice if you see your country end up in a list which I prefer not to live in, so that's not a nice thing. So that's why we present it this way. And if you go to the list, you see Switzerland, Scandinavian countries, Canada, the Netherlands, for some reason which I really can't explain, Belgium is part of it. So yeah, I'd say fairly obvious. So it looks pretty good. South Korea, yeah, it's good. Then the US, yeah, absolutely. So basically, there are quite a number of Asian countries that do quite well. And of course, there are quite a number of reasons for that. So Japan is obviously doing quite well. Very good healthcare, very good GDP. So yeah, absolutely. But there are also some strange things here. There are a number of countries which I would prefer not to live in. For instance, Turkmenistan. I don't know whether you're familiar with the country, but it's somewhere where you perhaps might not want to live, in the sense that Turkmenistan is governed by a president who is quote unquote elected for life, and at least the previous president had rather interesting ideas. So Turkmenistan is a pretty dry country. It has a lot of natural gas, which it exploits, and that gives it its high GDP. It also has a good healthcare system. So that's the explanation why it ends up here. But on the other hand, I wouldn't want to live there because one of the theories of at least the previous president was that since Turkmenistan is a dry country, it should get more rain. Okay, up to that point I can follow, but the way to get more rain is to plant trees. Up to that point I can sort of follow. That might indeed give you a bit more precipitation, but of course somehow you need to keep these trees alive before anything is going to happen. It's a dry country, your trees die. But that is not a problem if you are in a centrally led administration. Then you just make regional governments responsible for keeping the trees alive, which basically means that they water the trees. Okay, that's one way to deal with the problem. It's maybe not an optimal way since water is a limited resource, but okay, you can do it that way, or you can do it the smart way, which is that governors got the very brilliant idea of spray painting the trees green. So all the dead trees look green. Inspection was done by helicopter. The former president flew over the woods, quote unquote, saw green trees, was happy. Governors were happy, everyone's a winner. So yeah, well, basically that is a bit of an issue. Whether you want to live in such a country or not is basically up to you. I would prefer not to. Yeah. Yeah, exactly. So basically, there are things to consider with this data set. If you have correlation, then indeed it is something to consider. Actually, what you will see when we talk about when we briefly talk about feature reduction, is that you can actually apply feature reduction to this, and that reduction doesn't reduce the quality that much. So indeed, there are definitely correlations here. That is for sure. But again, that's the quality of your data set, and that's something that you need to consider. That's also why I choose an example that there are issues with the data and where there are issues with the algorithms which I use, just in order to point out things that are fairly obvious in this country, in this context, sorry, and that are much less obvious in more convoluted examples where you can't rely on intuition. Because the big advantage here is I have intuition about this. I can guess why Qatar is high in the list. I can guess why Saudi Arabia is quite in the list. So my intuition helps here. And that is something that's nice. If you have a domain knowledge, you're likely to be more successful in machine learning tasks. But of course, for many things, you don't have the intuition. Yeah, of course. It's just a measure. What is this whole happiness score worth? Yeah, it's a number. I mean, are the people really happy there, or are they really totally miserable in other cases? It depends. I mean, if you look at the countries and you're a little bit familiar with the countries, you know that people are actually, in some countries, rather carefree, while they should be extremely unhappy according to the happiness score. So it's just a number. Is it to go back to my one of the original slides when I talked about machine learning problems, is the happiness score the correct yardstick in order to measure happiness in a country? Question mark. But that is indeed something that you need to consider upfront. Is your yardstick the correct one? Do you have a correct yardstick? So that's also an illustration of that fact, and it's good that you pointed out. But indeed, that is part of the problem. And here it's all pretty obvious because you have intuition about these countries. You may have visited quite a number of them. So basically, you have intuition. But that is unfortunately often not the case. Okay, any questions about this part? Now we turn to deep learning and such. All right, no further questions or comments. So basically, deep learning you can do with many frameworks. There is TensorFlow, there is Keras, there is PyTorch, and so on. So personally, for many tasks, I like Keras or TensorFlow because Keras is part of TensorFlow and TensorFlow is part of Keras in a certain sense, because it gives you a high-level way of defining your networks rather than TensorFlow directly, or alternative PyTorch is also pretty low level. So depending on what you're doing, Keras might be the easiest way to get into things. Under the hood, Keras is using TensorFlow, or if you install TensorFlow, you will find Keras in there. So Keras is essentially, let's say, a friendly layer on top of TensorFlow. That's essentially the idea. That's also why I like it. I always like higher level things if I can get away with it, rather than low level things. That's also why I prefer to program in C++ rather than in assembler. That's the same thing at the end of the day. Okay, as you know, it's neural networks. So Keras defines many layer types, dense layers, convolutional layers, and so on. We'll see a number of examples, how they're used, where they're used, and so on. Okay, so let's first talk a little bit about neural networks, artificial neural networks, where they come from. Essentially, they got inspired by a biological network, which is our brain, essentially, our nervous system. So that consists of cells, which are called neurons, and those neurons send signals to other neurons via the axon. And at the end of those, the axon terminals are connected to dendrites, so the input, if you like, of the neuron. So that's basically the idea. So a signal gets sent to the axon and reaches another neuron. So what is important in such a cell is essentially the action potential, and that is basically determined by the ions in that particular cell fluid, you could say. So what you will typically see is that based on the chemical signals sent between the axis terminal and the dendrites, that potential is going to increase. And at a certain point, it reaches a threshold, and the neuron is going to fire. At that point, it will release a stream of ions through this axon that will reach the axon terminals, and that in turn will influence the potential of the neurons that are connected through their dendrites to the axon terminals of this particular thing. Okay, so the neuron fires, that decreases its action potential, and then it takes a little while, doesn't matter, that's a detail, to recover before it gets back to the ground level. So this is the ground level, and then the same thing happens again. There is input from other neurons via the dendrites. Potential increases, potential reaches threshold, the cell fires, etc., etc. So you get these spikes time after time, and of course the frequency and so on determines at the end of the day what you're thinking, just to put it very simple. Okay, so that idea gave rise to an artificial neural network, and essentially it's the same idea. You have the inputs, so those are essentially the dendrites. In other words, the signals sent into this neuron through the axon of other neurons. Okay, so each of this input is weighted, and that is at the end of the day just a linear weight. So we get x1 times w1 plus x2 times w2, etc., etc. And for good measure, we have a bias term, which essentially is just +1 times b. So that's just plus b in order to ensure that there is a threshold in this linear sum. And that's almost it. So that's this part I talked about. So the sum over I, where I ranges from 1 to n, where n is the number of inputs, of wi times xi plus b. Okay, that's not quite it, because there is the sigma in the formula, and that's the activation function. In the old literature, that would be called the transfer function, but nowadays it's called the activation function. And that needs to be, very often, a non-linear function. So that's important. And indeed, for this particular example, which is a sigmoid function, you see that indeed it is quite nonlinear. So basically, it has a derivative of 1 in x is equal to 0, and then it plateaus to 1 and to -1 respectively for large positive and negative values. Okay, so that is an individual neuron, which is totally uninteresting until you put them into a network. So each of these guys here in layer L2 is in fact a neuron as on the previous slide. So it takes all the inputs x1 up to xn. In this case, x is 3, n is 3, but whatever, and a certain bias. And we have a neuron, a second neuron, the third neuron in this L2 layer. And we continue the game further on in further layers. So basically, our input flows from the input layer, which I call L1 in this case. It determines the output of the second layer, which in turn determines the output of the third layer, which determines the output of the fourth layer, etc., until at some point we're done. So each of these things is a layer. Now, that's why it's called a multi-layer network. When is it called a deep neural network? When you have many of these layers. So there's nothing special about deep neural networks. They're just multi-layer networks with many layers. That's what it is at the end of the day. And of course, some special architectures, but as such, it's just many layers. Okay, so now the clue is, of course, how do we determine all those W's? Because we have very many of those. We have, if we have n inputs, we have m hidden units, then we have n times m, give or take 1 or 2, weights to determine, and this we need to do for each every layer. So we get lots of parameters. So how do we determine them? So basically that is exactly training. And an algorithm which has been around since the middle 80s, if memory serves, is called backpropagation. So how does that work? We initialize all those weights randomly. There is a lot of research whether you can do that a little smarter than randomly, but there's not that much difference in a way. Okay, and then we are going to do something repeatedly. And that's called the training epoch. That basically means that we're going to look at all our training data just once. Okay. And for all the input values and the output values in our training set, we're going to use the input and we compute the output. We can do that. We have the input, we have the weights. The weights are not correct, but we have them. We have initialized them. They're not, but nobody cares. So we will get output, and that output is likely going to be equally random as the weights at this point. But we get an output. So that's the forward pass. Then, of course, this is for supervised learning. So we have the actual output. So now we can compare the computed output with the training output. And basically the difference between those desired output versus the output you actually get is called the loss. And there are many loss functions that basically you can have the square difference and so on. But basically that's the difference. And then we are going to do a backward pass. We're going from the output layer back in the network until we reach the input layer, changing the weights, adapting the weights in such a way that for future run, the output will be more close, hopefully, to the training output. That's the idea. So that's why it's called backpropagation. The error which we compute using a forward pass is propagated backward through the network to the input in such a way that are changed in order to make future losses smaller. Okay, and as soon as the accuracy is either good enough, we stop, or alternatively, If we run out of compute time, we also stop. Okay. Because this is, of course, a pretty lengthy process. Now, one of the things which you might wonder about is, this is a minimization process, can we find the minimum? Yeah, of course, we can find the local minimum. It's as such not a big deal. But what we are not sure of is whether we have the global minimum. So basically, this is actually a very difficult process. So that's somewhat symbolically depicted here. So we want the error to go down as much as possible. However, in this particular case, we would be stuck in this local minimum. There are some other very interesting things, but okay, let's not consider that for now. So one task we might want to undertake is classification. So digit recognition. Now we have an image as input. That image represents a digit, a handwritten digit, and we want to recognize that written digit. Okay, so you could say that's regression because the result is a number. Yeah, no, actually it's classification because we just have 10 categories, 0, 1, 2, 3, and 4, etc., etc. So the input data is in fact grayscale, a grayscale image, and the output data is a category. Okay, so we get training examples, we get test examples, and so on. First approach, we have something that might be a bitmap, it might be a JPEG or whatever, but at the end of the day, we can't do anything with those. So we need to transform our image into numbers. And we can do that in several ways. One way would be to very simply take the grayscale values. Those range between 0 and 255, and create a very large array, one for each pixel, a one-dimensional array. Okay, and then the output data associated with this particular image would of course be digit 5. So that would be the idea. Okay, we can go with values between 0 and 255, or we can simply scale the lot between 0 and 1. So 255 would be 1, and 0 would be 0. Okay. Then the output array. The output we already know because it's a category, and we can use a one-hot encoding. So essentially, that would be an array of 10 elements where exactly 1 is equal to 1. Okay, and this can of course be a uint 8. All right, so we can do many things. One thing could be to have a multi-layer perceptron. And in this particular case, we have as many input as there are pixels in this particular image. And if memory serves, it is 28 by 28. I think so, which anyway in total would be 784 inputs. So each input is a single grayscale value representing a single pixel in this image. Okay, then we have a dense hidden layer with 512 units. What's a dense layer? It just means that any input is connected to any neuron. So there are connections everywhere. Okay, then we have an activation function, and in this case we don't choose a sigmoid function, we use a ReLU function, so a regularized linear unit. So I don't think I have a picture around in the slides. No, I don't. But there is a notebook with some. Okay, it will take me too long to start a notebook. Let me just simply, that will be easier. I'm just going to Google ReLU so that you can see it. It's actually very simple. As you can see, this is a plot let me just take this one, for instance. So basically, the value function is for values that are less than 0, it's just equal to 0. For values that are larger than 0, it's just equal to x. So that's your typical value function. So the blue one here, it's just a piecewise linear function, essentially. So you could say, okay, but that is not really nonlinear. Yeah, it is, because it's piecewise nonlinear. It's piecewise linear, so that's actually nonlinear, and that is actually enough. Which, to be honest, was a bit of a surprise for me when that was introduced, because back in the days we always used nonlinear functions that were continuous and also that that had a derivative defined, which ReLU obviously doesn't. But anyway, the advantage of it is that there is a question in the chat. Let me try and get there again. Yes, so indeed, that's a very good question. 512 is a hyperparameter. Also, the choice that it is a dense layer is hyperparameter. The fact that I use ReLU as a activation function is a hyperparameter, etc., etc. So essentially, the whole thing here is full of hyperparameters. And in a way, the architecture that I choose to have a dense hidden layer, followed by a dense hidden layer, followed by a dense hidden layer, and that there are 3 of them, is in fact also a sort of a hyperparameter, indeed. So there are quite a lot of hyperparameters here. Of course, each of the weight values of these 512 units, so 512 times 784, give or take a couple for the bias, those are the actual training parameters. But the 512, the fact that I use a ReLU, the fact that I use 3 layers and so on, and this number of units here, well, okay, that's not really a hyperparameter, I'll come back to it, but basically that actually means that those are indeed hyperparameters. Yeah, correct. Absolutely. So after my ReLU, the advantage of ReLU, by the way, is that it's very easy to process. I mean, the derivative is pretty straightforward. Computing it is really, really straightforward. So that takes very little execution time. If I have something sigmoid, like I showed in the original slide introducing neural networks, that is much more computationally intensive to compute. And that essentially means that your forward pass to your network is going to take considerably longer. So that's a big advantage of ReLU, and surprisingly, at least to me, it is sufficiently nonlinear in order to get what you want, which is, again, for me, a big surprise. Okay, so that's our first layer, dense hidden layer followed by an activation function. And then we have the same thing. Again, we have a 512 layer and a ReLU activation function. So basically, the second layer, this guy here, is going to have 512 inputs, the outputs of the previous layer. And it itself, it outputs 500, it has 512 units. So we will get 512 squared units. So that's something like 32,000. Okay, give or take again. Well, there are some more due to the bias, but okay. Then we have another ReLU function, and then we get a dense layer with 10 units. Okay, why 10 units? Well, 1 for each category, 1 for each digit. So in a way, that's what I meant, that it wasn't really a hyperparameter. In a sense, yeah, it's just the number of categories I want to predict. Okay, you could perhaps say, okay, I want an 11th category, which is, I'm very confused, but that would not be in my input data, so yeah, I'd stick to 10. Okay, and then we have a different activation function, a softmax activation function. And let me try to show you the definition of that. So that the definition of all these things is in the notebook, but it will take me a while to get that started. So that's why I prefer not to start a notebook right now. Okay, so softmax So I want a definition. Here's the definition. So as you can see, Zi is the category, and that is the value which I get for that particular unit. And as you can see, I use an exponential function weighted by a sum of exponentials. So if I were to sum sigma, if I were to sum over I here, I would of course get 1, because this is independent of I. I sum from I 1 to k, so I get 1. So that's cute. The output of my softmax is going to be values for each of these 10 output units, which range between 0 and 1. And the sum of those is equal to 1. So that's cute, because that means I can interpret them as probabilities. So in a way, you can view this, the output of this algorithm as something that gives you probability distribution over the 10 digits. And the output, due to the softmax function, is going to be much larger for the most probable one. So that's a very nice feature of this softmax function in the context of classification. Okay. So basically, as you can see here, in notebook 030, there is a lot of stuff about activation functions with quite a number of examples. And the whole notebook itself, where this is implemented, is in multi-layer perceptron. So basically, that's in 040. Okay, I'm going to start the network because I want to show you how it's constructed, at least for one. So let me do that anyway. Projects. Machine learning with Python, source code. Okay, now let's see. Activate. I'm not at my regular computer, so I have to be very careful because I didn't update things here, only on my laptop. So I have to be very careful here that I actually do the right thing. Okay, let me see. Okay, so I'll start the tab here. Okay. And I go to Keras. Oh, I did something. I don't know what I did. Wait. Okay, I did something very strange here. I don't know what. Let me go back here. I am here. Where's my Keras? I probably moved it into something. Oh, for crying out loud. Yeah, okay. I'll have to fix that, but it doesn't matter. All right, so basically here we are where we should be, and then we need mnist something. Let me see. Mnist data exploration, multi-layer perceptron. That would likely be the one I want. Okay, so just to show you how such a network is constructed, I want to briefly go through it. Let me increase font size. Let me hide this. So basically, we transform the data. So as you can see, this is all scikit-learn. And that's what I mean. Scikit-learn is still very relevant, also in the context of deep learning, even if you use another framework such as Keras, PyTorch, or your favorite in order to make more sophisticated models. But the whole pipeline thing is here. Let's not go there. We split into a training set, validation set, and test set at the end of the day. We do some verification, blah, blah, blah. And then we're going to start constructing the network. So basically, so normally I would do this from TensorFlow. So it is weird that this is not updated. Something with versions somewhere. Okay, I am surprised, but okay, it doesn't matter, because at the end of the day, nothing fundamentally changes. Okay, so one of the things that is really, really important is that you set your random number generator seed. And in fact, you should already do that before you do the split of your data set. As you can see, I'm going to split my data set, and I'm already setting my seed so that each time I execute this notebook, I'll get the exact same split between training set and validation set. So that's important to realize. Also, for reproducibility, remember that in fact, a lot of stuff is going to happen randomly, in the sense that, for instance, my initial neural network, my initial weights are going to be initialized randomly. If I do that differently, I would get a different output. So if I want reproducibility, I have to make sure that I set my seed for my random number generator. So this is, from a methodological point of view, quite important. So here we're starting to construct a network. It's going to be a sequential network in the sense that one layer feeds sequentially into another layer, and so on. Okay? So that's my model. And then I start adding layers to my model. So I add a dense layer with indeed 512 connections. And as an activation, I choose ReLU. Okay? And I have to specify the input shape, and that is going to be 784. Note that, very similar to many things in NumPy, I actually specify a tuple. And in this case, my input is one-dimensional, so this is going to be a one tuple. Okay. Then we add a second layer. Again, that's a dense layer. Since this is a sequential model, Keras automatically knows that the input for the second layer is going to be the output of the previous layer. So I don't need to bother specifying that I've got 512 inputs to my second layer. That's automatic due to the architecture which I choose here. So I don't need to specify it. And then finally, we have the last layer, and that's going to be a layer with 10 outputs, and the activation is a softmax. And again, Keras automatically knows that the input for this layer is going to be the 512, the output of the 512 neurons in the previous layer. Okay, so that's it. My model is now completely defined. Okay. One of the nice things about Keras models is that you can ask for a summary, and that basically gives you an overview of the number of parameters. So basically, we have 3 layers, dense 1, dense 2, dense 3. And you see the output shape. So the first layer indeed has 512 outputs, second has 512 outputs, third has 10 outputs. And you get the number of parameters. So in total, we would get something like 748 plus 1 times 512, and that should be approximately this number. Similar here, this would be 512 plus 1 times 512, something like that. And again, the same thing here. Okay, so this gives me the total number of parameters. So for this fairly simple model, I already get 670,000 parameters. And those, you might say, well, okay, there's total parameters here, training parameters. Okay, so why is that mentioned explicitly? I could decide, if I have a network that's already trained, to retrain it, but not all parameters. And that's important for things like transfer learning and so on, which I'll briefly mention later on. Okay, so this is just a summary. Model construction, 3 lines, summary, and now I compile my model. So it's going to be translated into code that is actually going to run on my GPU or on my CPU, depending on the architecture I'm using. And I want the loss function. I need to specify that, because basically that means that the backpropagation step is going to use this function to compute the loss at the output. And that's a categorical cross entropy. There is also, I think, a notebook that specifies that, but basically it's how different the actual output distribution, if you think of it in terms of probabilities, is from the actual output. Okay, then we need an optimizer. What is that? Remember, backpropagation is actually going to modify the weights depending on the error. So it's going to minimize things. And that's done by the optimizer. And that is going to try and find minimum given the loss function. So it tries to modify the weights in such a way that the current loss is going to decrease. That's the idea. That's the task of the optimizer. Remember that that landscape where we wanted to minimize a function. Well, that's the job of the optimizer. In this case, it is SGD, so stochastic gradient descent. There are many algorithms. A very popular one is Adam. So that is something that you will encounter quite a lot. And there are many variants. So basically, which one to pick? I don't know. Likely Adam is a good starting point, but not necessarily. So this is again a hyperparameter. Your optimization algorithm is a hyperparameter. And then we choose some metrics. And in this case, I want accuracy based on the validation set. Okay. Then we do a model fit. So we specify training sets, input, output, the batch size. I'll explain in a minute what that is. And then the number of epochs which we want. And we also specify the validation data. So that is my yardstick in order to see whether my training process is going the right way. Is it going to decrease errors? That's my goal from step to step. And aren't things overfitting? So that's why I need to specify the validation data if I can. And I want some verbose output. Okay, question in the chat. Let me try and get there. Yeah. Okay, so what are epochs? What is this batch size? So an epoch is an iteration through all examples. That's what an epoch is. Okay, so now we can do a number of things. I could say, okay, I have my input, I compute the output, and I'm going to adapt the weights according to that individual example. Okay, so then I would have the iterations which my stochastic gradient descent algorithm takes is again a different hyperparameter. I didn't specify it here. If I go back, I just specified SGD. I could specify here quite a number of parameters to fine-tune how that stochastic gradient descent algorithm works. In this case, it will use for each individual application of SGD some number, which I don't know, which is documented in the documentation, but which I have no clue about what it is, a maximum number of iterations for this optimization step. So the epochs does not relate to the number of steps the SGD takes. What it does relate to, together with the batch size, is how many times the SGD is in fact used, or rather computed. So, as I said, I could do that example by example. Each time I compute the output for a given example, compute a loss function, propagate it back using SGD through the network, layer by layer. In that case, I would have a batch size of 1. Okay, so that would be, on the one hand, very cost-intensive. Computationally, that would be very expensive because I need to run SGD many times, as many times as I have input-output pairs. That would be expensive. So it also has a second drawback. Typically, if you start to optimize on individual examples, you get a little bit of, how should I put that? One example is going to figuratively speaking, pull the weights a little bit to the left. The next example is going to pull it a bit to the right, etc., etc. So for several reasons, it's not a good idea to look at the examples individually. So what you typically do is say, well, okay, I want a certain batch size, so I want to consider a number of examples together. In this case, my batch size is 128, so I'm considering the loss function for 128 examples at once. And I'm going to, only then when I have the loss for those 128 examples, input-output pairs, I'm going to run my backpropagation. I'm going to run my SGD many, many times. So that's basically what that batch size means. So a batch size which is too small actually implies that there will be a lot of noise in my training process. It will go up, down, up, down, up, down. That is very, very annoying, and it will be very expensive. Of course, a batch size which is too large is going to miss details, because batch size actually averages in a certain way. Here I'm kind of, not entirely, but kind of averaging over 100 batches of 128 examples at once. So you can see that if I take thousands of examples for my batch size, that too much information is going to be lost and training will not proceed the right way. If I take my batch size too small, there will be much too much jitter and it will be very expensive. So that is actually the criterion to choose your batch size in principle. Unfortunately, nobody knows what batch size is optimal. There is a lot of research into that, but yeah, it's just not, no one knows the answer to that. However, there is another criterion, and this has to do with architecture and with literally running this. Because if you run this on GPUs, then you should make sure that your batch size fits into the memory of the GPU. Okay, that might sound like, okay, this is weird, but consider large images. Then, of course, each image in itself can be 20 megabytes. So if you have 128 images, that's quite a big amount of data. So then you might have to reduce the batch size a bit with respect to this 128 to something like 32, so that actually stuff fits into memory of your GPU. Because if your entire batch size doesn't fit into the GPU, you're not going to get any performance. That is not going to work. So basically, VRAM or the actual RAM, well, we're talking about actual RAM because even if the GPU has access to host memory, the data transfer still has to happen, and that's your slow factor. So if you think about GPU computing, your limiting factor is going to be data transport between host memory and GPU memory, because that goes, at least on almost all hardware, it goes through the PCI Express bus, and that has a very limited bandwidth with respect to other bandwidths involved in the system. So basically, virtual memory makes programming easier, but for performance, it may be more difficult to get good performance because you hide some complexity by doing things implicitly rather than explicitly. So that is actually what's going on there. Yeah, exactly. So I could show you my system, which is a bit more modest than yours, likely because it's a bit older. But basically, if I show you the GPU numbers, if I can find my GPU somewhere, yeah, here it is. So GPU 0. Then you see indeed I've got 8 gigabytes really for my GPU. It has 8 gigabytes physical memory. But of course, the GPU memory as such is 16 gigabytes, which is then a combination of host memory and actual memory on the device itself. But in this case, it's actually the memory on the device. So in my case, the 8 gigabyte, in your case, the 6 gigabyte, which counts, because all that virtual memory is skewed from a programming perspective, except that it's not special memory. It's just your average RAM of your PC. It still has to pass to the CPU, to the PCI Express bus, to the memory, the dedicated memory on your device. So the limiting factor is always the physical memory. The virtual memory is a measure which looks cute because it's a large number, but yeah, it really doesn't help in a way. So that only has to do with convenience for the programmer, not with any performance, unfortunately. And since you hide complexity, you need to realize that you're doing that. Okay, so that's in a nutshell the use of the batch size parameter. And then the number of epochs is simply the number of times I go through my entire data set in batches of 128. So if I have, let's say, 1024 examples, and I would have a batch size of 128 in this case, then I would have 8 batches for each epoch. So I would apply backpropagation 8 times to my dataset. Of course, if I really would have a dataset of 1024 examples, then my batch size should actually be lower because 128 is way too large for 1024. Anyway, with 1024, you're not going to get anywhere. So it's a hypothetical example, but it's just to make the arithmetic in my head a bit easier. Okay, so that's the purpose of these parameters. And then you see that if you run this, here's some outdated thing, but yeah, that's not something I can help because that's a library thing. But then you see that this is the first epoch, and you see that you get the time it takes. So as you can see, it's 12 seconds. And you get the loss function, you get the accuracy, you get the validation loss, and you get the validation accuracy. And you get that for each epoch. So each line here is one epoch that goes on for quite a while. Let's not go there. We end up with, at the end of the day, we end up with an accuracy of 99% and a validation accuracy of 97%. So if I have a very high accuracy on my training data and a significantly lower accuracy on my validation data, then I do have overfitting. This seems quite okay. This is really in the same ballpark. So my actual testing error is most likely going to be around 97% if my split was okay and so on. So this looks quite good. So we have some overfitting, that's clear, but it's not dramatic. So this should be more or less okay. Okay, so we can actually plot this. And then you see that we get a training error versus the validation error. It decreases monotonically, which is always reassuring, but which need not happen. It might be that actually the error decreases, and then suddenly it increases, decreases again, it plateaus, and then after quite a while it starts decreasing a bit, and so on. So this is very nice. And you will see this because this is a very simple network. But if you go to more complex networks, then this function gets quite a lot uglier in general. Okay. So this was the loss function. This is the accuracy. Accuracy goes to 1, as you can see. The loss function goes to 0. Okay, great. We do have a bit of overfitting. If we look at it at the test data, you see that it's indeed very close to the validation error. We have 97.5 as an accuracy for the test data. We had 97.3 for the validation data. So that is really very close. So indeed, the validation error represents, is a good yardstick for the actual performance of our model. Okay, so you can save a model. That's very easy. It gets saved into an HDF5 file, which is a particular file format which is very convenient to store models in. There are different formats for serializing models. So yeah, you can use whatever you want, whatever is more convenient. Okay, so we do have some overfitting because indeed 99% is larger than 97%. So what can we do to avoid overfitting? Well, one of the things we can do is add dropout layers. So now I've added 2 dropout layers between each of the dense layers. I've got 3 layers, so I get 2 dropout layers. And the number I specify here is the number of weights that is going to be set to 0 randomly. And this avoids overfitting. Of course, now we get more parameters. Well, no, we don't get more parameters because basically dropout layers don't have parameters. So basically that remains the same. All of this is the same thing. Nothing changes. If we run that, then at the end of the day, we see that now our training data is 98% accuracy, and the validation data is still of the order of 97.5%. So as you can see, they're more close together. Better, because that means less overfitting, less specific weights for the training data. This is the plot, as usual. Nothing interesting is happening here. If we look at the test data, then you see again it's very similar. So here on the test data, nothing much happened. It improved a little bit, but not significantly. So adding dropout layers, for instance, may help alleviating problems with overfitting. As I said here, they're absolutely not dramatic, but also just to illustrate that you can actually do that. Okay. So again, it's always a good idea to compute a confusion matrix. So basically, I have a very nice graphical representation of that. Dark blue are very high values. So basically, if I have dark blue on the diagonals, that's very nice, because that means that these predictions, if I have a, say, what is it? If I have a tree here as input, then I have a very high probability that tree will be predicted. So that's good. Why is a confusion matrix interesting? Well, you see it here. For instance, if I have a 7, that easily gets confused with a 1 and a 2, or more easily gets confused with a 1 and a 2. And that's, of course, if you look at the shape of the actual digits, that's not so unlikely. A 7 badly written resembles a 1. A 2 badly written can resemble a 7. So this is nice from the perspective of doing analysis of why things get a little bit confused. Here, for instance, a 9 and a 3. A 9 and a 4, okay, that is a bit more exotic, but still you have this shape here. It's not round, but you see where this is going. So basically, this is a very nice way to initialize this. Back to sensitivity analysis, yes, you can do that. So basically, let's train a couple of models with different input, and let's compare the output. And then you see in this particular case, if I look at the training, the validation, and the test results, that actually they're very close together. So these are the losses, these are the accuracies. So the initial conditions at least play a very small role. You could also play here not only with the initial conditions, but you could also play with parameter values. What happens when I replace the dense layers by layers with 1024 units. How does my accuracy change? How does it change when I have 512 layers and so on? So this is a way to actually accommodate that. Okay, so that is quite straightforward. Let's move on to a better approach. So basically, this is not a deep neural network. It's only 3 layers. This is a classical multi-layer network. But you see where this is going. I can keep on going in such a sequential model and add more and more layers. Okay, so this is an evolution of the number of layers. Surely you've already seen it. And basically, what you see here is the prediction accuracy over time and the winning models for certain context contest over time. And you see the number of layers plotted here. As you can see, there is quite some some evolution. Now, the important thing of deep neural networks is that part of what they learn is in fact the features. So if you look at machine learning back in the, let's say, 70s, 80s, 90s, then a major task of someone who was doing machine learning was identifying features. What do I mean by that? For our country example and the happiness score, that was pretty straightforward. It's just numbers. But if you have an image, what are your features? And so people sat down and thought about their data set and tried to figure out which features to give to the neural network as input. For instance, how many vertical lines do you have? How prominent are they? Do you have something like closed loops somewhere in your image? Things like that. And of course, you can already see I have some difficulty just coming up with examples. Yeah, people had significant difficulties coming up with relevant features because I can figure something out, but does it make sense? So basically, that's one of the advantages of deep neural networks. Low in the network, so close to the input, you get the low-level features. So things like horizontal lines, things like vertical lines, and then higher up, those very primitive features are combined into higher level features. So if I have vertical lines and horizontal lines, I might actually have a square. But I can only decide that I have a square after I have identified that I have vertical and horizontal lines. Square might not be there, but if it's there, then I need to know that I had vertical and horizontal lines in reasonable positions. So basically, you go from low-level features to higher-level features. And then we're still talking geometry. And then at the end of the day, you end up with semantic features like an object, which is there, a category of an object. That's basically the idea. To debug the layers, it depends on what you mean by debugging. The shape sizes and so on, it's just not going to compile. So if you define a network that is not, let's call it syntactically correct, it's not going to compile. And then you will get error messages in the style of layer 5 and layer 6 can't connect because number of outputs is different from number of inputs, these kind of things. So that's kind of given in a way. You can't mess up too badly, otherwise it's just not going to compile. Okay, that's the advantage of using those frameworks. They do a lot of the heavy lifting for you, and that kind of mistake is okay, maybe still easy to make, but also easy to detect. So that's the advantage of that. Okay, so one of the things that also changed besides the depth of the models, so the number of layers, was types of layers. And a few of them are really new when compared again to the 90s and the 80s. Some of them are just adaptations of things that were invented then, but that nobody used because they were computationally too expensive. So in the context of image processing, convolution layers are quite important. The dropout layer we already discussed. Recurrent layers were invented a long time ago, but no one could run them. So now they are part of the standard toolbox. So how does that work? What is convolution? So a small matrix, and you run that over a big matrix, each time computing a matrix product here. And that's just an element-wise product. Just product of these matrices. And that is going to give you a number. So in this particular So basically, for the 5, it would be like this. This kernel is different. This has ones on the other diagonal. So it's going to contain these diagonal lines, so the ones which slant the other way. Here would be one. Again, the same example, but now on the tree. So here's a little bit of a diagonal line. Not so much. Here a little bit, but overall not so much. So basically, the other one would give you. Oh, why did I switch those? That's a little bit weird. Should have. Okay. Anyway, so the other diagonal, there are more than I already thought that it's going to be correct. So basically, you see that these particular convolutional kernels are going to allow me to detect diagonal lines. Okay. So now these matrices here, of course, I've created by hand. And I can say, well, okay, this is going to detect diagonal lines. Nice. But that's also part of the learning process. So what we're going to do now is to not consider our data as one-dimensional, but as two-dimensional. And of course, in the context of image processing, that makes a lot of sense, because if I go from 2 dimensions to 1 dimension, I lose all spatial correlation. I don't have the notion of a lower and an upper neighbor in a trivial way. In principle, the algorithm can still figure it out, but in general, you lose a lot of information, which you have to figure out again in a much more complicated way than with a convolutional network. So here in this case, we just do a similar thing, but we go from a one-dimensional, from our image to a two-dimensional array. Apart from that, it's the same. Okay, now our architecture is different. We have 28 times 28 inputs, one for each pixel. We have a convolutional layer with 32 filters. And our filters are 3 by 3. So that means, in the previous example, that we would have these small matrices, 3 by 3. And we have 32 of those. Each of those can be learned. So we don't specify upfront that we want to look for horizontal lines. No. We let that be determined by the training set, by the algorithm. Okay, then we get a relativation function, blah, blah. We have a flattened layer, which turns these two-dimensional things into one large one-dimensional thing. And then finally, we have a dense layer with 10 units. And then, of course, our usual softmax. Okay, let's quickly go to the corresponding notebook. Just to show you the infrastructure, the construction. It is of course quite similar, but CNN, that's the one. Oh, there are 2 of them. Why are there 2? This is CNN. PBS, no, that's JavaScript. Okay, no, this is not. Okay, So let's skip this part. It's the same. So model definition. As you can see, I specified the number of filters, the number of classes, then the filter size, 3 by 3. And again, it's a sequential network. I add my 2D convolutional filter, same as before. Nothing special happens except for the padding here. Because of course, if you are at the edge of the image, what should you do? And there are several padding algorithms. Which one you pick depends on your particular application. Okay, the input shape is just given by, this is a tuple which I determined before. It's somewhere here. That depends on my data set. Can't find it. It's somewhere, sorry. Can't find it immediately. Doesn't matter, it basically specifies the size of your input. So it will be 28 times 28 at least, and then an additional number. Okay, and then we have our activation function. Notice that in this case, I add the activation function as a separate layer. So where for a dense layer, you can optionally specify the activation function in one go. For convolutional layers and in general, you can just do that as a separate layer. Doesn't matter as such. Okay, we have the flatten, and we have a dense and a softmax activation. Okay, again, we compile our network, we do the training. Now, I would have been very happy if I had the number of parameters here, and I don't, so that's slightly annoying. And I also don't have the output, which is also slightly annoying. The problem is that if I start to execute this, I'm busy for quite a while. Okay, so that is, I have to run it at some point and store it in my repository, evaluate it, because this is annoying. So I would just look at it. If memory serves, the number of parameters is significantly lower, and the accuracy is actually better if memory serves. But it's quite a while ago since I executed this notebook, so just try it out for yourself. It runs happily still on a CPU, so you don't need anything special for that. This is a small problem, so you can easily run this on a CPU as well. Okay. So that was a little bit about convolutional layers. And what I traditionally did was then turn to another problem, a text classification, because that's a different kettle of fish, in the sense that if you think about text, the problem is that you don't know how long it is, the input. Some text is short, some text is long. So you can already feel that there is going to be an issue here. Another issue is that words that are spaced in a sentence or over multiple sentences far apart still influence one another quite a lot. For instance, this is an example with movie reviews. And of course, what I could do is start a film review with "This is sarcasm," and then write glowing praise about the movie. And of course, if you as a human were to read it, then you know that "this is sarcasm" means that you have to kind of invert any expressed opinion about the movie, because it's likely very bad. However, if you don't have that context, if you don't have the contrast between the praise, "This was a brilliant plot with genius plot genius plot twists," and you don't correlate that with sarcasm, then your conclusion will be entirely wrong. So what you need, in a way, is memory. And that memory can be provided in several ways. So I'm going to, let's see, what's the time? Ew, this is very bad. Okay, so let's talk a little bit about how we go from this input to something that we can actually meaningfully compute with. So how do we go from a text to numbers? There are quite a number of ways to do that. But at the end of the day, what it actually boils down to is that you are going to have a vocabulary. You are going to take a certain vocabulary, so a set of words, and each of those vocabularies is going to be represented by a vector. And the simplest way to do that is with a one-hot vector. So, for instance, A, the word A in English would be represented by 1, 0, 0, 0, 0, etc. The word Z would be represented by 0, 1, 0, 0, 0, 0, etc. The word book would be represented by 0, 0, 0, 0, 1, 0, 0, 0, etc., etc. Okay, so basically that means that the vectors which we need have the length of the vocabulary size, given the number of words in English, which is, if memory serves, something like 200,000, that would be a very long vector. Of course, if you look only at commonly used words, then for English you get to something like 5,000. Okay, but the problem is that you get very long vectors. That's unpleasant, that's a lot of data, that's a lot of connections, because weights, because remember, for each input we have a weight. If we have 200,000 input vectors, it means we have 200 weights for each neuron. So that's going to be a lot of weights to determine. So that's unpleasant. And also there is zero relationship between our words, because there is no correlation between one hot encoding and the next. The only information that you get is that it's a different word. Whether or not there is a relationship between those words is, yeah, you can't know. There is no correspondence. So that's why people came up with the idea of word embeddings. So you still start with these very large vectors, but from those you compute a dense representation. So the original vectors are extremely sparse. Only one element of the vector is 1, all the others are 0. So you want to go to a dense representation where most vector elements are non-zero, and on top of that, a vector which is quite a bit shorter than the original one. So basically, you replace binary information by information encoded as real numbers. And of course, given that there is much more information to be coded into real numbers, that can actually work. But you want something more. Besides a more compact representation, you also want that if two words are semantically related, so if they somehow either mean the same thing, or due to their meaning regularly occur together in the text, that these vectors that represent them have a large overlap. Or conversely, if two words have nothing in common, they don't mean the same thing, they're never or hardly ever used in the same sentence or in the same text, then you would like that the distance between those vectors is very small. So basically, you would like that the vector distance somehow corresponds to the semantic distance between the words. Okay, so that is the principle of a word embedding. And so in this case, we have two documents. The first document says, okay, Obama speaks to the media in Illinois. And the second says, the president greets the press in Chicago. And of course, if you analyze lots of texts, if you compute many of such vector representations, then of course you start to notice that Obama and president are very often close together or in sentences that basically express the same kind of thing. Similar for greets and speaks. Similar for Chicago and Illinois. Both are entities, both are geographical locations. And media and press are also closely related. So basically, in that vector space which we're going to construct, or in those vectors rather, that we're going to construct, they live in a vector space in such a way that the vector distance is hopefully as much as possible determined by the semantic distance of the words themselves in the given context. So in the set of documents, this embedding is computed for. So this is a pretty important notion, because during the training, you're actually going to use the context. It's not just the word. You're also going to take into account words that precede the given word and words that succeed, that are after the given word in the sentence. So that is important. And basically, the training itself will discover relations between words, but also between subsequent words, between one word and the word that follows it, and so on. So basically, that is the idea of word embeddings. And basically, that means that if you have a sparse representation, a one-hot representation, the embedding is actually going to compute that dense vector for that particular word. That's the idea. Okay. The rest of the slides here are about recurrent neural networks. And let's say up to a couple of years ago, recurrent neural networks would be the way to deal with tasks like sentiment analysis, like translation, and so on. Everything that had to do with sequences, so also, for instance, DNA or RNA, that would be the way to go, because those could remember. They kept context of things they'd seen before, and they can also operate on arbitrary length sequences, both for input and for output. Okay, nowadays, so if you're interested, just have a look through the slides. It's reasonably explained how this works. I'm not going to go there right now, because essentially, if I had to do such tasks at this point in time, I wouldn't use a GRU or an LSTM anymore. What I would use most likely is a large language model. So basically something GPT-like. So that's why I'm not going to these slides. I'm not going through LLMs now because of lack of time. There is a different training about large language models, specifically on how to run them on, let's say, modest hardware. And in that training, I also explain about LLMs. The key point about them is essentially that is essentially attention mechanism. So basically, it is a way to learn the relationship between a word and words in its context. So essentially, it will learn that if a word occurs a couple of words after a certain one, and it's preceded by yet another word, that there is a certain semantics involved. So that's what these languages, what these models are going to be trained for. The architecture is tuned to train this. And this is the attention mechanism. And yeah, basically, there is a famous paper which introduced this, and the title of that was "Attention is All You Need." So that is actually the subject of a different training, and I'm not going to start explaining LLMs here. I originally planned to, but I don't have time, obviously. But if you like, I can give you the link to the repository if you're in a hurry. Otherwise, the training is scheduled for somewhere end of this academic year, I think. I already gave it, but that was a VIB event. So Given that I'm not on my computer, I'm not logged into GitHub, and GitHub is annoying me since I need my phone to authenticate, and the app on my phone needs to authenticate. So I'm here physically a bit in a how shall I put it? In a catch-22. So I need a different computer to actually access my own GitHub repository. However, conveniently, I can still find it, I hope. Get rid of these. Now, where is my repository? Here. Okay, this is the list of repositories. And then I want tools and AI tools. So this is the relevant one. Okay. Do I do? Okay. So this contains some material about LLMs, an introduction to what LLMs are, and specifically how to run them. Okay. So here's the link to the page. The link to the repository is here. So basically, you can find that easily. All right. So I'd like to conclude here. Yeah, there isn't. Well, it's 1 o'clock, and there certainly isn't time for more. So basically, I hope you enjoyed the training. If there are any further questions, please feel free to ask. I think I did everything in the chat, but if there's more, let me know.
Yes, can I ask one more question?
Yeah, sure.
Yes, so could you provide some guidelines or recommendations on how you would manage keeping track of the different models you test and their performance? So would you typically create a data set of the models you test with their hyperparameters, architecture, and performance, or how would you handle this in practice?
Yeah, indeed, you need a training set. In order to do that, you probably, depending on the algorithm, need a validation set. And you should, of course, also have a test set. And what I would do, if I would have enough data, is to have a training set and a validation set in order to do training. Then a test set to see whether my algorithm is not way overfitted. And then have a different test set, which I never use, except to compare the different models. But then, of course, you need quite a lot of data. But the problem is, yeah, choosing on the basis of data alone should always happen on the basis of unseen data. Because otherwise, of course, you are mixing things, and then you kind of get in trouble. I hope that's somewhat of an answer to your question.
Yes, thank you.
Then there is a 3-part question by Elena. Only your switch regression. No, you can use any algorithm. So, for instance, to deal with perfect separation. I don't quite get what you mean by separation in the context of, because ridge regression is only for regression, so that's not classification. So while if you use the term perfect separation, that leads me in the direction of classification. So I'm a bit confused here. So yeah, okay, but group membership is classification. So ridge regression is really predicting numerical values. So I don't think ridge regression is ever used in the context of classification. So then indeed something like logistic regression can be used, or support vector machine, a multi-layer neural network the Bayesian algorithm. So you have many choices, but ridge regression is not really one of them, I think. I don't think it, I've never seen it used in the context of classification. Then the second question, when testing, okay, LOOCV, so that's a cross-validation thing, clearly, but frankly, I don't know. Because I don't know what, I don't know exactly what that is. It is some cross-validation thing. So the answer is yes, you can use cross-validation simply to assess whether you have overfitting or not. That is entirely okay. Personally, if I have a choice, but that depends on the size of the data, then I prefer to have training set, validation set separately, and then my test set. But that is a little bit old school nowadays. And of course, you can't do that when you don't have enough data. You can only have that luxury if you have enough data. So if you don't have enough data, you're always going to do some cross-validation. So essentially, you are going to use your entire data set for training. No, sorry, not your entire data set. You're going to use your entire training data set purely for training and checking for overfitting using cross-validation. That's then typically what you would do. And I'm assuming here that LOOCV is some sort of cross-validation algorithm, but again, I don't know it. I'm not familiar with that. Yeah, so basically, which values are more important and so on. Indeed, ridge regression is not going to do that for you. Things you can think of then is really, let's say, sensitivity analysis with respect to the different parameters. This is something you could do. Or you can try dimensionality reduction and using a technique similar to those. So indeed, you won't get that out of ridge regression. It's not going to do that for you. There is a method, well, an algorithm agnostic way in order to determine these, in order to do that type of analysis which you want to do. Let me quickly look it up. It's a nice tool. There are examples in the repository. Source code. Let me see. Where is that? Let's also increase the size a bit. This is weird. I'm missing stuff in my repository. I don't think I'm working with the correct version of my repository because there is missing data here. Well, there is missing source code here, to be precise. What's this tool called? Of course I can't remember. Bloody annoying. And I remember too little of the name in order to start guessing and looking for it. But the idea is that you indeed do a sensitivity analysis, but without changing the model, by changing the inputs. So basically, you mask certain inputs, you replace them by dummy values, and you see how that influences the prediction performance of the model. So you have training data, you have a trained model, you apply the model to masked versions of your input data, you still know the output, and you can see which of your input values influences the outcome the most or the least. And you can get them in order and so on. So that's basically the way to do that. There is a very nice tool for it. Normally there should be something in the repository because I made an illustration. I remember that, but I can't find it in the repository right now. So that is weird. It's possible that I forgot to merge or whatever. I have to check. But that would actually be a good way of doing that. If you send me email, because I can find, of course, I can find the name of the tool, but not now. So if you send me email, I'll be happy to send you the name. Then, okay, guns, yes. There is somewhere a small example of a gun. So basically, it's essentially the same thing. The only thing is that you have two networks. So basically, you play around with the loss function. I have an example somewhere, but probably not in this repository. I should have a look. But I'll try and find a different tutorial because it's better. Rather than give you a code example to find you a tutorial, it should not be difficult to find one. Okay. Yeah, absolutely. So many algorithms are in fact implemented in R as well. So ridge regression, there is no doubt that there is an R function for that. That is a given. Let's put it that way. Okay, then I think I answered all questions, not necessarily successfully, but yeah. All right. So if no more questions, we'll conclude here and perhaps see you in another training.